what I think you guys will find is that we came up with a concept that, although may not be fully finished, is well underway to come into a point where it could replace this lathe machine and be able to wrap the magnets the way we wanted it to be wrapped.
So the reason that they told us that they need it is because currently what they use, they have an ancient lathe that they've repurposed for this purpose. It's huge, it's old, and they wanted something that was smaller, more mobile, and overall a simpler way to do it than the lathe that they had in place. So the big things they cared about were the ease of use, the safety, and transportability of it, as well as the size. That's all.
Alrighty, coming up with the project parameters, we had 3 meetings overall with Hazlet, and those first 2 meetings especially were heavy on going over the parameters for this project. And we also got to talk and work with the operators that would be operating this machine to get their input to make sure that we got what we needed. So we have quite a few parameters. One of those was to have an automated traverse system that could locate the fins that we wanted to be located. And then once those fins were located, to have the stepper motor put everything in the right position to then start the wrapping process. We needed this machine to hold at least 2 rolls of Kevlar, so each of these strings goes to a spool of Kevlar. So we needed to develop a system that would work for our contraption. An automated start, something to where we could have the servo motor start at a home position to keep everything nice and simple. We needed a max rotational speed, so we got a gear drive DC motor, one with hopefully enough power, we haven't tested it out yet, to rotate one of these spools, which weigh at least 300 pounds. So we needed something with enough torque to do that, and to do it well, but without having to go too fast. So something nice and torquey. We also needed a contraption here that could support that 300 pounds. So 300 pounds is a lot of weight, and one of the ways, or the way we came up with that solution is by using aluminum extrusion, which the mechanical guys will go over later. Not only was it sort of a clean solution, simplistic in design, but it could support that weight, which was verified through simulation testing on MATLAB. Not MATLAB, excuse me. What's the software called? SolidWorks, thank you. And we needed something that was mobile, ergonomically friendly, something that could be moved around when not in use to save space, and then that could be pushed into position while also being able to support the 300 pounds and being stable and not very tippy. And those were the main parameters of our project.
Yes. All right, so for our actual design, we ended up splitting the process the project into 3 main sub-assemblies. We had our linear traverse system, which actually was the actual movement, which moved back and forth across the roll. And then we also had the roll fixturing, which includes the gear motor on the far left there. And over here, there's a fixture that holds it in place. So that whole system is one. The whole system on the back is one. And then the last one we were going over is the table design to actually hold the roll, as well as the Kevlar housing underneath the table.
All right, so this is the first mechanical subassembly, which is the linear traverse system. And it has 7 main components, and as you'll see, they're all labeled up here. I'd like to start with one of the main ones, the 1 and 2, which is the rack and pinion and stepper motor, which are labeled right here. This is the rack and pinion. 2 is the stepper motor here. and that interlocks along with the linear slide 3. You can see it's connected here with a bracket to the stepper motor itself. And then for the 4th is the actual Kevlar routing head. Now this is the head that will route the Kevlar from the bottom of the assembly and then to these rollers here and then down to the actual backup roll itself. Then the 5th one is the fin sensor here. Now this is an important part because this is what actually automates the system, and it will detect the fins along the roll, which you'll see later, and that will allow it to sense the fins, and then the program will do what it needs to do from there, automating the process. Number 6 is the cat track, and you'll see this right here. This is an important part because we have moving wires, and we need a way to move the wires without getting caught or catching anything. And then finally, the 7th main part of this linear traverse is the actual control panel. And the wires go from the cat track into the control panel, which has some components here, mainly a button to switch on and off the stepper motor, the green push button, which is the operator's button to get the assembly to start moving and automate the process. This potentiometer dial here allows the operator to control how fast the stepper motor moves, and this allows them to have a jog so they can move it where they might need it or send it home. And then finally is the fuse, which is basically just, if something goes wrong, the fuse will blow, easily replaceable. And those are the main components of the linear traverse mechanical subassembly.
Okay, so for actually fixturing the roll, we ended up going with a gear motor. It's got a 23-to-1 gear ratio that allows us to have enough torque to actually spin the shaft up to a 300-pound shaft. In order to get the power from the motor to the actual roll to spin it, we have a shaft coupling system, which is just like a shaft adapter, 1 inch to 5/8 inch. And this part in the middle here is actually something that Hazlitt already uses on their setup they have now. So we decided why change it if that works. So we can slide that right into our coupling, and it allows the shaft to spin. And then on the opposite side of the motor, we have the pillow block assembly, which is on a sliding locking plate that allows the system to be modular so that we can have different size backup rolls on the table because there's multiple different sizes. And then we also made a custom parts for actually raising the gear motor up to the right height so that these are even with each other so you're not tilted or anything. We ended up going with steel tubing for this, so this doesn't look exactly how it is now, but it's the same idea.
All right, so this is the last part of the mechanical subassembly. So this is the table and cart structure, and this was made from 60 by 60 millimeter aluminum extrusion. And this is important because it's very modular. It's mainly for prototyping, which we were kind of going for here. But we have triangle brackets up here. They're a little bit hard to see, but you'll be able to see in the actual thing once we get there. And these prevent the roll from falling off of the frame because that was an important part which we talked about was Hazlitt. And the caster wheels, so they're locking caster wheels, so it's very easy to move around and kind of if they need to store it as well. And then finally, the cart that houses the Kevlar is down here. And this just makes it really easy to replace the Kevlar. And we didn't want to quite put the Kevlar on the frame itself because we would have had to make a system to try and,
So for the electrical design for this circuit, we went with using a STM32 microcontroller to drive everything because I was already familiar with the programming for it. It has a very effective HAL system. It had sufficient I/O for our requirements and was plenty powerful. And it's a lot cheaper than a PLC would have been for the same application. For our motor driver, the DC motor is a 10 amp motor, so we used a H-bridge MOSFET circuit. There's 2 P-channel MOSFETs on the high end and then 2 N-channel MOSFETs on the low end. We went with this instead of a 4 N-channel setup because the circuitry is much more complex for a 4 N-channel H-bridge. Down in this corner, we have the circuits for the front panel. So there's a speed control potentiometer, there's a push button that's the main control for the whole system, and then there's the 3 indicator LEDs. All the indicator LEDs run at a higher voltage than the STM can put out, so those are toggled by a MOSFET on the low end. And then we have the e-stop circuit. This isn't a circuit board, but we have 3 e-stop buttons that go through the e-stop relay, and then the relay will tell the STM to stop all motion if the e-stop is triggered. It's not a very complicated circuit, but it's important.
All right. Here for the board design, in the top left corner there, for all of the high voltage stuff, you can see some thicker traces, 3.5 millimeter traces were used, just in case the DC motor did want to pull a lot of amps for some reason. We have a 2-layer board design. All of the blue traces you see here, those are cut onto the bottom layer of the board. All of the red traces, these would be jumper wires that would be connected through these vias, physical wires soldered onto the board to make those connections. And for repairability, we soldered headers. I soldered headers onto these pins right here. And for the ICs on the other side of the board, they're little IC holders that you can solder in place so that you can place and replace any ICs needed very easily. And yeah, that is the overall board design.
So the program for this system, I used a state machine diagram control for it. So it follows this state machine diagram right here. It starts by waiting for the push button to be pressed so that it doesn't just start moving when it gets power. And then it will go all the way to the home sensor, after which it waits for the button to be pressed again when it's ready to start being rolled. After which the stepper motor will move, counting the number of fins that are indicated in the program. Right now we have 2. So as long as it detects at least 2 fins, which is the very first fin, and then the fin after that, it will carry on. If it detects less than 2 fins, that means that it's reached the end of the roll and it's carrying off. So after that, it goes back to the right before the home state. So it'll wait for the push button to be pressed again, and then it'll go back home. If it detects fins, it'll wait for the green button so that the operator can affix the Kevlar string, get everything ready and set to go. And then after the green push button is pressed, the stepper motor will go 3/8 of an inch to the left, and then 7/8 to the right, I think, or 7/16, 15/16, I think. But and then it'll wait for the push button to be pressed so that the Kevlar can be cut, and it will enable the potentiometer control for the motor. And then after all that's been done and the push button gets pressed again, it just goes through the whole cycle again to do the next set of fins until it gets all the way through the roll. To do this in the STM, we had to use free RTOS so that I could have a thread for the motor control and for the stepper control to control them both at the same time. So the same state machine controls both of the threads of the STM32. And for the over travel sensor and e-stop, there are external interrupt pins on the STM that are triggered by them. And the e-stop causes all of the motion to be stopped. So it halts the motor driver and it sets both of the N-channel MOSFETs to pull it down to ground, and it stops the stepper motor from moving. That is everything.
Okay, the bill of materials here, we ended up spending a total of about $5,700. Some of the biggest components were definitely the two motors that we had to buy. Else the rack and pinion weren't necessarily cheap either. Yeah, so we have listed out all the purchase parts we have. We have all the manufactured parts we have, so we'll be able to put them all in a document so you guys have them. And yeah.
All right. The beginning of this semester, we went over planning quite a bit and how to plan for a project. Although never having partaken in such a project with a large scope like this one, our planning wasn't as thorough as we coulda, woulda, shoulda made it. We thought that we would be able to design the circuit and then based off of that, pretty much immediately get the parts that we needed within a week or two, have those ordered and start working with the programming, at least on the electrical side. But what we kind of ran into is selecting parts took quite a bit longer than we anticipated. There were some parts that were utilized in the schematic for the electrical circuit that we needed replacements for because those parts aren't made anymore. And when it came to motor selection, we definitely wanted to take our time and make the right selection so that we didn't have to worry about returning anything. That took a couple of days just for the motors themselves. And when it came to building the structure itself, there was a lot of help from Hazlet, a good amount of back and forth going over the design, making sure that it would be able to handle the weight of the roller, and that it would be safe enough to kind of go through and build it. And so that was something that we kind of anticipated would go a little bit quicker than it did. But there was a lot of work on the back end coming up with the structure and making sure it was safe enough for our project. And then with the PCB on my side, I was a little bit unfamiliar with the software that I used. So getting used to that software took a little bit longer than anticipated, but once I got used to it, I was able to make some reiterations of PCBs, one that would work for the machine we have over in Randolph, and then a version of the PCB that would you'd be able to order from a company like PCBWay, that would have a PCB with a mask, making things easier to solder on the back end. And so overall, the Gantt software we used was a good way to sort of give us a plan, but there were a lot of changes that were made to this plan, a lot of unforeseen stuff thanks to the scope of the project. But in the end, we kind of did as much as we could do with the time that we had.
All right. So here's some future improvements that we wanted to think about and wanted to introduce to the Hazlet team. And some of these improvements include automating the string cutting, automating the string adherent to the actual roll itself, having a welded steel frame, which was mentioned in the meetings, a wire harness improvement, which you'll see it's the harness is a little bit messy, but it's kind of a learning process. So, and then additional fin wrapping. So up to 4 fins at once would be a big improvement. But overall, I think we hit a lot of our goals for this project. And these are some of them kind of like a final assembly list, which would be, a step further down rather than just the prototype itself. So yeah, those are some future improvements. And then here is our slide on lessons learned. And now this one's pretty important. You can read it if you'd like, but some of the big ones are standardization. So we are all new to kind of working as a team and doing projects as engineers. So one of the big things we learned is standardization of parts and hardware. Now, this is a big one because it really is like most of the time you should be choosing a system of measurement, whether that be imperial or metric, and then sticking with that. I think a lot of our parts kind of had separate, so like the stepper motor would have imperial holes while the DC motor would have metric. But I think better looking into that would be important for later projects. And then earlier parts ordering was a big one. So like working with the Hazlet team to kind of get the parts here quicker and, you know, the main assembly parts so we can have some more time to troubleshoot and other things. Troubleshooting is also one of them, you know, giving that time for the troubleshooting is very important. I mean, as any engineer would know, there's going to be problems in every project. So you got to include some time for troubleshooting. And then finally is like testing earlier. Now this kind of includes with like the earlier parts ordering and stuff. It would be nice to be able to test earlier so the electrical, you know, side of things would be able to see what problems there are, see if the code needs improvement or changing. And those are like the main big lessons we learned as a group here with our first big scope project as engineers. So yeah, those are our lessons learned. And then, yeah, so any questions or comments, please feel free to ask and we'll answer them to the best of our ability.
So you mentioned further improvement. So do you think that people are going to do something about that, or particularly for projects like how to sell?
They probably
That's why
Steve.
you answer.
I'm just gonna give it to Steve. Yeah.
No, we'll take it and we'll modify it, but we wanted to get a good prototype set up first. So this was a great way to get us started and get the initial thing, and then we'll take over. We have fabrication abilities for like the welded steel frame that they mentioned, some of the different things, but we'll probably be over the course of time modifying and evolving.
Any other questions or comments?
Yes. Go ahead.
Oh yeah, so I see lessons learned of what to do differently, but being students here and this is a student project, what was something that maybe one or each of you like took away from this that was really enjoyed learning? Like was it assembling the frame, working on the motor? I don't know, was it part of the project that you guys really enjoyed?
So for me personally, I really enjoyed the modeling. So using SolidWorks to build it up from the ground was really interesting to me. It really was like, take an idea and a problem, figuring out how to solve it, and then building a machine from ground up. That was a big takeaway for me.
All your designs like come from on a computer to in front of you at real scale is very rewarding. So, anything?
I mean, for me, everything I did was on the computer, so I didn't get to see it all come to reality. But I did really enjoy putting what we've learned in like our power electronics course in implementing a state machine in a program. Actually getting to see that do the state machine felt a lot more significant just doing it in a classroom.
Yeah, I agree with what Weston said about getting to see what you made, creating the PCB, and then, getting it back from Mr. Marceau, who brought it back from Randolph for us, was pretty exciting. Something physical to kind of get to put time into now versus just spending all that time on the computer. It was also nice learning the KiCad software. We haven't spent too much time in like learning design principles for printed circuit boards. So it was nice to kind of dive into that a little bit more. Yeah.
Good question. Thank you, Sam. How do you guys feel about working with your partner? Very sure question. How easy is it for you?
Well, I would say it's more stressful to do a project for somebody else than it is to do one just for yourself, for sure. I don't know if everybody else agrees with me on that, but that's definitely how I feel about it. It's rewarding to do, but it's a lot more stressful than it would otherwise be.
Yeah, I think I also. I mean, it's. I don't even know what I want to say. But you just want to be able to deliver something that they're happy with. That's one of it. So. Yep. And if you're doing it for yourself and then you're done with it after, you can just put it away and never think about it again. But this is like it's going to be put to use somewhere. So. Yeah.
First of all, thank you so much for working on this project. Think about this. Likewise, what's your combination to prevent noise from coming in? What accommodation?
So primarily that's compensated by the STM has built-in pull-down resistance pins, the biggest reduction for noise to have. Additionally, it's on a separate ground rail from all of our high power components, which reduces the amount of noise that actually gets to it to prevent any sort of random activity. We did have some issues with noise early on in our assembly that were a result of running the stepper motor at the highest power that it could. But we didn't actually want to run it at that high power. It didn't need to. So that was fairly simple to solve. It can run it between 1.5 amps and 10 amps. And we had just had to power, and that created a lot.
Situation not expressed by the operator.
So the program on the STM requires getting power cut to it and turned back on before it will do anything, and then it will start back at the top of the state machine. So you have to press the power button, and it'll start going back home.
That's exciting. I appreciate all your efforts and meeting all you folks and the energy you put into it. Really encouraging for us.
Thank you.
Thank you.
Thank you.
This project. It's been a great one. I know you guys have put a lot of time and effort into it. It's been an awesome learning experience, not only for these 4 students right here, but everybody else in the class. And I'm going to take your lessons learned slide and show it to the next group of seniors in the fall, and let them take that away. But thank you very, very much. They do have the machine set up in the physics lab. It's a little challenging to bring it here, so we'll be going over there for the demonstration part. But I also wanted to introduce our lab technician extraordinaire and today's videographer, Kevin Orth. Kevin has been working printed circuit boards for the past couple of weeks and cranking them out pretty much as fast as the LPKF can generate them. So I do appreciate all his efforts here, and he's going to be taking some well-deserved time off in a few weeks here. Also want to introduce Ralph Esposito. He's the program coordinator for electrical and electromechanical. Ralph, can you put up a hand or stand up or say hi? But let's venture over to the physics lab and take a look at the tool after that great presentation. Thank you.
Check, check, check. Check, check, check. Hey. I'm trying to find them. I don't know where they went.
I feel like I missed.
Hey, where's the physics lab?
It's
I went there and I was supposed to film them and I can't find them.
yeah, it's kind of it's a little bit of
You know where Robin Julian's office is?
I don't know anything about this campus.
All right, I'll show you.
I can. I know
Oh,
where
okay.
it is. Yeah. Because we're over here and it's over there, right?
Yeah, I'll show you guys.
Okay.
It's
Okay. Then. Be back for this.
I'm constantly taking up Eric Whitebody's time.
no worries.
Me too.
This no,
It's a club.
I forget to image this place all the time.
Oh.
It's in a weird spot.
Yeah. How's the Wi-Fi in the courtyard?
Good. There's actually an access point right there.
Oh, nice.
Yeah.
I just don't know if because I'm using NDI.
Oh.
I don't know. Plug in. That's device. I just know that it works when I'm on the same router.
Same area, yeah.
We'll see if this works. Looks like we missed
Right
the.
there.
Thank you.
Yeah, of course.
Hey, we found you.
Ah.
You want to start over?
Sure. All right.
Been running around. I have no idea where this room was.
You like that? How's the box? Oh, dude, have power. I just wanted to show the home sensor. I just wanted the home to do something.
The other thing too, you gotta have a really good set
Turn on those. Not on. My turn now?
The gear too.
Oh, yeah, but that's now.
Yeah.
Oh.
Hopefully I let it go far.
Yeah. Oh.
There you go. It was totally fine this time.
So what's happening?
So now it's looking for a new fin, but then it didn't see one, so it's done now. Then it won't go back home because it doesn't want to, but.
Start it again?
Start it over. Oh, you want me to just, I'll do it.
Yeah, so it's going to its home position now.
Yeah.
And once it reaches its home, it waits for the button press, for the operator to press it, for it to go look for its next position to start the wrapper start.
Now
So it's looking for fins right now, so I let it go a little bit.
Yeah, let it go a bit farther. It's pointing closer to the home sensor.
That's probably good. So let's say it senses one fin here, another one. So it's got its two fins. It's going to go back to the middle. This is where the operator would set up their Kevlar string coming through the frame. They set it up, they soak it, adhesive that it goes through, and then they stick it on the roll that would be spinning right here. Then we'll go ahead and start the spinning and start wrapping. And then it starts the process. So it's wrapping, goes that way, goes back, and then ends again in the middle for 2 layers. Yeah, and then they start that process.
I think the problem is that I forgot to put a flyback dial for this, so it's not going to do anything until I reset it. And then
That's it. It'll just go back to its start.
yeah.
Thanks.
Yeah. I can do a couple more things.
I was just gonna say. So you guys fired this up?
It's not just
Right away, you start working?
Yeah.
Really?
Well, so I realized that the problem is this right here, we just barely put this in. I forgot to put the flyback.
Yeah. You want to just tie it, it's got wheels.
How you doing, Kevin?
Pretty good.
Good. Thank you for the back and forth. That last reference picture helped me a lot. I understand how the Via's good work with the jumpers. That was good. Thank
Yeah. No, it took some troubleshooting.
All right, so just so you
The one designing the frame, yeah. Weston helped me put them together, but
These are just one straight bar. These were cut at an angle. And yeah.
oh yeah, cut those ones on a bandsaw. Got the angles. They're not perfect, but you know.
Did you cut them in Hazlet or?
I ended up cutting at a different manufacturing plant. Yeah. No, it is. I was getting on top of it and like, you know, put my whole body weight so it can hold.
Okay, that's good. Because yeah, you put your body weight on it, you move it. That's
Oh yeah, my full.
that's like double weight.
Yeah, you like the car?
Yeah, what the fuck?
Oh, it's for the Kevlar. So that's where the Kevlar rolls. Yep. And then it'll be
Wait,
wrapped.
after you wrap it?
Or oh no,
That's like where the materials holds it.
Oh, okay.
It gets fed through the holes in
Yep.
the system. Up to those holes.
Yeah, it's not about that. It's about learning.
Just watching.
This right here, is there an aperture here?
We're talking, we haven't done that yet, but that's definitely something that, like, there's not something key with this, it just needs a shroud of some sort. Ambient light, that's a sensory part of notice.
I'm trying to find a photo of the stuff.
The Kevlar.
Yeah, just like a 3D cylinder, it's a knockout.
Yeah, we have them in that slide.
Yeah, we didn't have a roll, or else we would have brought one to try it, but we didn't have one.
Nothing's calibrated at all.
I'm getting some of that.
We had discussed that right there.
Okay. Half a box each? Yeah. Okay.
So, the
Let me get some of that. Everything.
I don't know what Wes and Noah's way of dealing with that was.
Tail stuck.
I know it's one of the concerns that we could do this
Yeah, just don't expect them to like shut up in your box.
That's fine. I'm glad the presentation.
a few different options.
Yeah, we can get a tail stuck.
I appreciate that.
Honestly, for how much pressure needs to be put on, you can honestly just use like a screw or threaded rod type thing to be able to give it a little pressure.
Wait, I like what?
Like how felt being that tail stuff.
Oh yeah.
It wasn't really hot.
Oh really?
This stuff, after drilling through this stuff really hard.
Like worse than this.
I don't know. It was not worse than the belt stuff.
No, the belt's
It's terrible.
Give it enough friction to turn. I was a little concerned.
Yeah. Shit.
You have to have pressure on it.
Yep. We had to manually drill most of our holes, so it was like.
going to give it to the freshmen. So if you want to take some for later, that's fine too.
Oh. I gotta zip it though, 'cause it's like 35 meg. I've got a flash drive here too. Want to do that? Oh yeah, I just run it. Maybe you leftovers, I'll take it. I don't know if it's gonna clinic, but don't worry. Yeah, I'll just go make it good. Oh yeah. Well, that's Michael's drive.
I got it from the back room. Yeah. Maybe I got some bad bits.
You need a meal too? I have it on the
So is there any kind of warranty with that tool?
Our machine?
Yeah.
Absolutely not.
Oh, okay. All right.
Call Weston Black.
Oh, and you also told them we don't deliver, right?
Yeah. No.
Yeah. Okay. Yeah. Oh, where'd Hal go? Send him back to the lab. See, yeah, isn't giving a presentation better than taking a paper exam? Way better, yeah. Jerry's still out on that one. All right. Ooh, I may have to get a copy of that for my next presentation. Oh, it is? Hmm. Hmm. Is that?
No, I can just
It's not.
use this
Oh, okay.
computer and do it.
Okay. No worries.
I got it. Forward, backwards. Okay. So the way it works is you want to point it up at the screen name. Yeah. Here. So hold the top button. Yep. I'll probably just say arrow. Yeah. Not accessible. On the flash. Yeah. And I sent it an email too. Okay. And if not, it's on my computer right here. So. Oh, well, that's easy. Well, I just wanted to have a slide up while I did the demo. We have that with us. Oh, there it is.
I blame it on Windows, but.
Oh, it's like when I loaded it to OneDrive, it's like 15 minutes up. Test, 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 test.
around.
Yeah. Well, so I'm Sam Cowan, and this is my senior capstone here. What I chose to do is a programmable seeder. And what that is if a seeder, if you guys don't know, is an implement that's used in agriculture to literally drill or place seeds in the ground at the desired location. Programmable implies I can control when and where those seeds are dropped. And then if you're curious about neon dirt, that's just my little name I like for my little ag tools that I come up in my head. Just a fun little name. And if you like the flowers, I grew those. I have quite the agricultural hobby, or should I say gardening hobby. So all of these are from my gardens over the years. Where am I aiming this thing, Kevin? I see it on my screen, yeah. Yeah. Great. So mission statement, kind of a high-level goal. It's a programmable seeder, as I said, and it's a tool designed for small farmer empowerment. That's kind of the overarching goal. When I say small farmer, if you guys have been to farmers markets here in Vermont, a lot of them are 1 to 4 acres and are what are called market gardens is the common term, or also human scale agriculture. So they may use heavy implements like a tractor infrequently, but most of the work is done by hand with hand tools. And then commonly, this is a mechanical seeder just for reference. So you can see this is a 6-row seeder rolling along the bed, placing 6 rows of seeds at once. This little picture kind of gives you a scale of these farms. You know, again, 1 to 4 acres is the size. And then also another hand tool implement for cultivation there. So very human-centric, very small tool, dominant. Yeah, and how does the tool work? You know, the goal was set out. The tool will use an encoder to determine its position as it rolls along the bed. And based on that encoder and periodic polling, it will drop the seed where programmed. I did want to emphasize the use of compostable and highly recyclable materials. I can speak more to that as we go along here. That being said, there were some project limitations that I had to pivot and use plastics. And just to highlight that, microplastics and plastics are a very serious concern in soils and can accumulate in plants and subsequently up the food chain. So the overarching goal was to reduce plastic. Unfortunately, you can see a lot of my components are PLA, which is plastic. Great for prototyping. I would not be comfortable using that in an agricultural setting as a final product, but good to get there halfway. So more specific project design goals. This is actually like, how do I want the seeds to be placed? Planting bed width. I picked a 1 meter maximum, so my seeder can place seeds over a meter width of a planting bed. With embedded 75 to 30 inch bed, and that may sound odd, but that is the standard market garden bed. So most small scale farmers have a 30 inch bed. So even though this tool is a meter long, it has the row spacing for those market garden beds. So the common planting patterns that most farmers would want to use. I don't want to make a tool that doesn't integrate into a farm that exists. I want to make a tool that can do more, but also work with what exists. Row-to-row spacing, I chose a minimum spacing of 5 centimeters. So across this meter tube, there are 20 holes spaced at 5 centimeters. Why that? That's kind of a common spacing, 2 to 3 inches for baby greens. So if you get a cut lettuce mix, a lot of times it's not like one head of lettuce. It's thousands of lettuce seeds that they go and cut with scissors, or like what's the word? I can't think of it, but anyways, it's cut as it goes along, and it's many plants versus one is the takeaway. Programmable, I want this to be pattern agnostic, in the sense that you are limited to the actual physical holes in the vacuum tube, but beyond that, you can time the planting pattern. And at a simple point here, we have offset, so it alternate rows, and I wanted to point this out. If you look at the slide here, and if we're moving from the bottom of the slide to the top of the slide, this first row is in line, and then you can see it offsets, and then the second row goes back. So that's offset planning. That's something that mechanical seeders can do, but very expensive models and quite limited. Most can't, and that's kind of was the proof of concept for this, is doing initial testing with an offset pattern.
And then, yeah, back to my point of farmer empowerment. You know, I don't want to make us problem and then find a solution. I want to do it the other way around. So I want to hopefully create an implement and a tool that is helpful to farmers and is not a burden and is not just another piece of technology that, you know, runs 6 months and is then thrown in the garbage. So just kind of looking at my project timeline, I will say this, 80% of projects happen in 20% of the time. So even though this looks very neat and orderly, I would say project management was changing week to week. I think one of the larger things was, as Thomas and that gang spoke to, is the project scope, defining my parts, what would work, what not, took a lot longer for me than I thought it would. But this is a rough outline of what actually happened. So mostly design, mechanical assembly, and you can see a design component in those later weeks because I had to pivot, do some prototyping that just, I wanted to use wooden wheels and it didn't work. But I'll get into that more later. Project bill of materials, around $760, I'd say, with other minor fasteners and implements, closer to $800. A lot of my structures from a company called Go Builda. I chose that because I'm not a mechanical student, I'm an electrical student. So it's very modular, user-friendly, and also just, as those folks said, really good for prototyping. And then in terms of, we'll get into the other subcomponents soon. I just wanted to point out the section in red. Those were pieces ordered that I just wasn't able to incorporate. This had been designed to be a standalone unit that runs on a 24-volt lithium iron phosphate battery pack, which I have the cells, but due to time constraints and other things, that wasn't possible, but will be pursued in future iterations. Going kind of into the system, power supply, as I spoke to, it was designed to be a 24-volt nominal lithium iron phosphate. Some really cool headway up in the top right here, 31-120 cells, so 38 millimeters in diameter, 120 millimeters in length, 3.2 volt nominal, and then 8 amp hours. So they're quite large cells. And I chose those cells because this fan I have on this unit is a 67 watt fan, and I wanted to have at least 4 hours of use for this machine if that was planting. Power regulation, 12 volt DC 10 amp buck regulator. That steps the battery pack down to the 12 volt fan voltage, and it's dedicated to that. And then beyond that, I have a 3.3 volt buck, which is the logic power supply used by the Pico, my microcontroller, and the encoder, and all other sensors on board. In terms of actuators, I have two FAM001 stepper motors. They actually are the exact unit that you would find in a Bamboo A1 printer. I chose them because they kind of fill this niche range of power, where they're in a NEMA 17 format, but can run up to what I now know is 1.2 amps. So I didn't know how much torque, how much energy this system would need, so I over-spec'd it for that reason. Position encoder, I think you guys are all familiar with that. I use the AMT 102. That's on our prototyping boards that Kevin has made for some modules in our labs. Rotary encoder, that's the KY unit, again, something we've used in the class. Raspberry Pi Pico is my microcontroller. Just through my other work, I've really liked the Raspberry Pi ecosystem, and it's great. And then I tried out a new OLED. So it's still I2C like some that we've done here, but it's a bigger format, 128 by 128. And specifically chosen because it's actually quoted by Adafruit as being very good in bright daylight. So in the context of a farmer's using this in the sun in the field, I want them to be able to read what they're seeing. And the one thing I want to take to point out here is the fan here. That fan took me about 2 weeks to spec. Most vacuum seeders use what you expect, a vacuum, which at a low level is a shop vac, and at a high level are $1,000 vacuums. So I wanted to find a solution that was smaller and more power efficient, but still needed to pull a good bit of vacuum. And from my research in this little yellow box here, this little fan can pull 13.4 inches of water. So, you know, if you imagine a tube of water, it would rise 13 inches in the pipe. And that's kind of just a unit of measurement. And to give you an idea, most seeds are in the 5 to 20 inches water to be collected to a vacuum tube and adhere to it. Most seeds are less than 15. The above 15, you're talking about big seeds like wheat and corn, which was not the design of this implement. Structure, as I said before, I went with the Go Builda ecosystem. It's all M4 screws and fasteners. The actual structural frame is 20 by 20 hollow 4-channel extrusion. The tubing I used is both for the rollers, which are my wheels, and also the vacuum tube. Originally, it was designed to be wood, and if you look at these photos here, I had tried to manufacture these shafts with a neighbor and also with Mike down in Randolph, and it just wasn't possible. They just kept tearing out, and I couldn't get a smooth finish or something consistent. And it was also quite a challenge to center this rotor concentrically, because we did put it on, and it sure had a lot of wobble. So I had to abandon that idea, and I went back to these 2.5-inch outer diameter tubes. And the nice thing about that, just thinking about farmer help modularity, is they're all the same. So in the future, I would love to make them all just different size planting patterns, so a farmer could switch out to the vacuum tube that they desire for that planting goal. Got to step forward here, can't read my slides. Yeah, and again, the design goal I wanted to point out, this is one of those points that I had to pivot from, a late design and change order, was I had to move away from these white cedar wood rollers, which I was very excited to source locally from a mill, Koning Cedar up in South Burlington, but alas, it didn't work. So I had to go for aluminum and then also PLA for some other parts that would have been made with cedar. Vacuum tube assembly, a little more focus on this. These are some photos from down in Randolph campus where I cut and actually used these, Bridgeport, I used one of those paths to put 300 holes. Took 2 days and 8 hours, but I got it done. And so it was exciting to learn that process and also manufacture something myself. What I'm calling the hard-coded planting row pattern is actually like the seeds that how do I say it? It's the planting position points I chose along the tube. 1 row, 2 row, 3 row, 4 row, and 6 row. Those are very common planting patterns for farmers, so that's the reason for choosing that. And I highlight at 6 row, most mechanical seeders stop at a 6 row seeder. Like that's the largest unit you can buy for a 75 centimeter bed, and they retail for $3,500. So to go beyond that, I have a 10 row. There's only one that can do 12 row, and that's actually even a smaller format. It's 12 rows, but really in the format of what the 6 row would do. And then 20 rows. It was just like I wanted to reach a meter bed planting pattern, to have a total meter of width. Not that you have to use it, but just to have that ability. And that is also closer to a larger California row cropping, which is 3.5 feet spacing. Drivetrain, again, this was all new to me, so I didn't know how much torque I'd need for this vacuum tube, so I decided to use a 3:1 gear ratio to step up the torque just in case I needed a little more oomph to get that wheel to go around. Turns out it rolls at 300 milliamps, so good bearings, good design, but over-spec'd. On the other I just want to point out, you have to have the vacuum actually exit the tube, so I couldn't put a shaft on there or shaft to hold it, so I use these skateboard pulleys as idlers, so the vacuum tube can roll on those. And there is a radial bearing set within this purple piece, and that actually allows the vacuum tube to rotate while the ducting, I should say, stays still. What I'm calling the seed extractor arm, which is really the implement that knocks the seeds off the vacuum tube once they've been sucked on, is an 8mm aluminum shaft, a Go Builda components, pillow block bearings, and then custom 3D parts. I'm going to pass one around in a second, the demo, but they are used to knock off the seeds while also ensuring they don't collect any other ones, hence why they're so narrow. Again, driven by an FAM 001 stepper directly, and then totally plenty of power. One thing I learned from this design is 8mm aluminum is quite soft, so that shaft is not as straight as it was when it started. So learning pattern. So would probably try to change that to steel or a thicker bore to avoid that problem. And then on to hardware prototyping. This is kind of where the project reaches lab bench testing. This is my little lab at home. That is the complete assembled cedar with the integrated sensors and actuators and microcontroller. So just a breadboard layout here. But just to point out here, this is the encoder on the back wheel here, which is fed to the microcontroller, which makes decisions on when to actuate the 2 steppers and drop the seeds based on the program. OLED for user interface, rotary encoder for the user to select the program and move through the state machine, and then also 2 TMC 2209 stepper drivers, which Analog Devices makes, and Adafruit makes the breakout boards for that. Hardware prototyping again, this is the user interface, a little deeper dive into that. again used the Adafruit grayscale OLED with the explicit design goal of having something legible in bright sunlight. And it's also just a personal interest because it has grayscale, so it has a hex, hex values. I can have 16 different grayscale settings to have a faded look in the OLED. The rotary encoder that was on hand, I just used what I had there. I will say it's a very bouncy signal when I put it in the picoscope, so I had to make an RC filter. Even then, it's still a little unpredictable. So when I say room for improvement, I would probably pivot away from that specific encoder. Motors, drivers. Originally, I started out with the Polo Lu 3731 36 V8, and what that is it can accept a VIN of 8 to 50 volts. So I wanted to keep 50 volts because future iterations I may have designs to add a 48 volt panel to that, so I wanted to have that ability to run on that. And it's also 3.3 volt logic native, so I can interface it directly with the Pico, which, if you guys don't know, the Pico is 3.3 volt limited. It can't handle 5 volt. It'll brick the little device. Adafruit, as I said, the TMC2209 by Analog Devices is what I had to pivot to because I fried that first board. It was either back-powered through a diode or just one of my initial testing where I did see quite a current surge on the bench, but a learning experience. And again, the stepper's the same bamboo motor. Vacuum fan, as I said before, is that high static fan. The other thing I didn't mention is it's high flow. So you want a high static, high flow. There's no seeds on the vacuum. You want the fan to move a lot of air so it can still maintain that vacuum because it's pulling a lot through those holes. So that was a balance, and again, I was really happy with what I spec'd for that. It has a 60 millimeter intake. Unfortunately, due to the limitations of the vacuum tube, it's 40 millimeter throughout, so it doesn't use the total volume of the fan until it reaches it in the 3D part here. Software development. Build environment, I did this in Linux command line using CMake build, and really is the Raspberry Pi Pico SDK. That's what it's designed for. My editor was Helix, debugger was a GNU debugger, and then a Raspberry Pi debug probe that Kevin provided for me for debugging. Serial monitor, how to get my printfs out, that was in Minicom in my terminal. And then the primary library is beyond my main program. This is a demo, it runs in a main.c, but I also needed OLED.h, which I ported from Adafruit's library to C for that OLED. And then also really exciting is Pico example, which is part of the Pico development environment, provides a quadrature.pio. And the PIO is really cool. It's a piece within the microcontroller that is separate from the CPU. So essentially it can read the encoder count at extremely fast rate because it runs its own state machine while not taking any time away from the CPU. So anytime my program wants to call the count at any point, it can grab it. And it's also can track to like 10 kilohertz, way faster than this machine would ever roll. So that was exciting to use. Helix is just a little picture shown there, the debug probe, and then this is just a Minicom printout. You can see it's rolling through my state machine and some testing I did. We go calibrate, state test, and so on. And I will get into that in a little more detail. Here is my state machine. How it works is upon power up, it goes to boot. That's just initializing the GPIO pins and doing its safety checks. It goes to calibrate. And calibrate is important because my steppers don't have a homing location. They don't have an index. They don't have a stall point where the sensor can detect, hey, stepper, I'm at home position. So the user actually aligns it with 3D cuts in the tube, and that allows them to switch out the tubes in the future, but also just one less sensor and a simpler state machine. So they press the button, they roll the shaft to where it aligns with 2 lines, and it's as simple as that, and they do that for both the vacuum tube and the seed extractor. After you move through calibrate, there is an optional position function. That would be if you wanted to change the orientation of those extractors. So that it will literally move the shaft to that extractor position. You can put your piece to that location, fasten it, and so on and so forth, all the way through 360 degrees of rotation. Right now I'm using 90 degrees of that shaft, but you could do it all the way around to really give yourself a lot of options. But position is optional. You can move right through it. Program, that's what it sounds like. That's where you just you select what do you want to do. This is 9-row spacing right now. So, or excuse me, 8-row spacing. So it plants 8 rows, offsets 8 rows, and goes back to the original location, just like that picture I showed you before. And then after a program, you hit it and it goes into its sample loop, and that's a while true loop, so it won't exit that unless you press abort, which is just simply pressing the button. That goes back to calibrate. But in the sample loop, how that works, this is my little subsystem over here. The roller reaches the drop point, which is based on your row spacing. So say it's 5 centimeters. If the count and your math reconciles, hey, I'm at drop point, then the extractor actuates, gets into position to catch the seed, and then the vacuum tube rolls past it to knock off the seed and also position itself for the next run. And then the extractor arm returns so it's not hitting any seeds in between the next drop point, and then we increment to the next drop point there. So really simple state machine that way. Yeah, and then so this is actually what you would see on the OLED. I'm going to go back to this slide when I do the demo just because you're not all going to be able to see it, the OLED, but it's the same format here. And yeah, I guess I'll do the demo at the end, but project challenge is mechanical. I'm not a mechanical student, so I learned a lot along the way. No CAD experience. Example A, this is a meter tube, but I have 10 centimeters that I didn't think about. That is blocked by my stepper motor, so that'll be for Mark II. So I would say not having CAD experience or working with someone that does was definitely a challenge. And then in another mechanical component, I had the idealized goal of using cedar wood. I really wanted to use stuff that if it breaks off in the field, you don't have to sweat it. You can let it just sit in the dirt. Unfortunately, wood can warp over time, and if you need something to stay very straight, that's not possible. So electrical, stepper failure, blew one stepper, so just a learning experience there. But I was excited to know that after hours of debugging with Pico, I could actually identify the problem. So even though I knew it was broke, I knew how it broke. The MOSI line on the SPI stayed high, so something in that, I think it's open drain, must have fried. So it's nice to know what went wrong and then to know that it's actually broken, and that's when I pivoted to that different stepper driver. Scope creep, I think that was the biggest one for me. You know, I'm like, oh, I'll build a vacuum tube. Well, what is a vacuum tube? You know, it's like, that's a plenum. What's the size of that? How are you going to pull on that? What's the flow? You know, these are something that we would model in control systems. So I think oversimplifying some of my ideas kind of came back to bite me in the sense that you really need to flesh these ideas out so you have discrete steps that you can you know, count on, because again, yeah, I thought it would just come together, and all these problems I hadn't thought about came up with that. Yeah, and that's that fit in later, you know, it's like, oh, you know, it's mostly good, that vacuum. You know, I had to print distinct 3D parts because I didn't think about where exactly that would sit on the axis. So yeah, scope creep and just having not an explicitly defined mechanical structure definitely was a challenge for sure. Future iterations, you know, I think of maybe Evan told me the story of just the CEO of Beta built their first plane. Is like, yeah, it works, but we need to rebuild it. And that's kind of how I feel about this. Aluminum was good for prototyping. The 4-channel was great for prototyping, but I really think I would use a flat bar steel outline with actual, you know, send cut send fittings drilled in so I could attach just to it and really reduce the complexity of that machine. Electrical, that rotary encoder is poor to say it nicely, so upgrading to something that's debounced internally, is weatherized for the farm environment would be one of my next goals. Integrating the 24-volt battery I have is definitely a next goal. And then also, this is lab bench breakout. I think I'm at a point now with this testing that I'd love to integrate those actual ICs onto one master PCB, just for getting rid of this rat nest of wires. Software, right now I only have one planting pattern programmed into that, so just expanding what a farmer could use so they could cycle through 1 row, 2 row, 3 row, whatever they need for that specific goal. And then ultimately when I get to a point with Mark II is just I really want to give this to a farmer around here and see, hey, is this a useful tool or is this something that's a headache? You know, like, because it's one thing for me to think this is useful, but I would really love some real world feedback on that. Thank yous, I got a couple. Michael, thank you for all your help along the way. I felt very supported. Barry, I really appreciated your mechanical insights and helping me solve these problems in my head, and I didn't know what a stub axle was till you explained it to me. Mike's not here, helped me manufacture the tube. I have done very little manufacturing, so that was very cool and empowering to know that I can machine some of my own things. Ben Lesgarden, that's a good friend of mine. He helped with some of the trickier mechanical 3D components, and I really couldn't have done some of those without him. Evan and Amelia, I work on the Wisdom project with them. They taught me the Pico SDK, how to work with the Raspberry Pi, how to debug in Linux. So I'm very grateful to just have that ability to work with that ecosystem. And yeah, the VTSU electrical department, you know, all my classmates, staff, it's been a really great experience here. And then finally, my family, my dad, and my partner Lindsay. You know, I really couldn't have done it without them. So a big thank you to them too. So yeah, if you, I'll answer questions, and after that, I'll go to the demo. Ben? Yeah. Yes, most definitely. I have a neighbor that has a 4-foot rototiller, so once I get this working, we're gonna go try it for real. Yeah, no, yeah, no. So I would love to get to that point where I can actually do a field test. Yeah, that's part of the plan. Just didn't quite make it there in this semester.
Sam, do you have a partner or a farmer that's willing to do this with you?
I haven't reached out yet, just because mostly I don't have a machine that I want to give anybody yet. But I have a couple in mind, just in my area. Trying to think of the name. Footprint Farm. They're in Starksboro. It's just a local farm. I'd say start local. Just it's an easier way to build a relationship, and hopefully they'd like to try it out. So if I get to that point, yeah, maybe Footprint Farm would be my first point I would reach out to.
More time, would you want to like try and make it more renewable, sustainable, and maybe like more modular and be able to?
Yeah, I mean, this is my personal interests, hobby, passion. So this project will definitely continue after this. I will get this to the point where I can test it in the field and hopefully get it to a working product. You know.
I think that's awesome because it's like it's clearly important to you for it to be sustainable and be helping our farmers. So
Yeah, and that was a compromise. You know, I can't deny how amazing a 3D printer is for prototyping and rapid prototyping, but I would not use that in a farm field. So to see if I could make these parts somehow translate to wood components in the future would be a big goal. You know. Yeah, I mean, it's I don't have the exact science, but to put it at a high level, it's just microplastics from any plastic are already in our soils and bioaccumulate through the plants, and then even more to a higher order magnitude to us. So really, it's just managing contamination. You want your food to be free of plastic. You know?
Sam, is there a seed size limit you can use?
Yeah, so good question. So this is that was a manufacturing limitation. So the smallest bit I could get was a 1.4 millimeter bit. We tried 1 millimeter. I snapped 2 of them, and then we went to 1.4. So yeah, if the seed is smaller in any of its axes, smaller than 1.4 millimeter, it will get sucked into that tube. So yeah, that's the limitation there. I would say practically what it can do is beets, kales, carrots, pelleted seeds like lettuce, and then my test seed, which I'll show in the demo, which is a nice big round seed, so it makes it easier for that to actually adhere to the tube. The other thing too is if it's not the size, say like beets, I don't know if you guys know the seeds, but it's a very angular, blocky with voids in it, so it wouldn't seat nicely to a vacuum tube. So you know, maybe higher vacuum, maybe different shape, things to play around with. But the initial mark was for pelleted seed because it's uniform and round, and hopefully the easiest thing to work with.
Thank
Kevin, can you roll me back a couple slides, and so I'll do the demo now? Yeah.
These are the holes for seeds?
Yep. I gotta use that one. No, you're good. Yeah, you can spin that top one. It doesn't have a sensor if you want to check it out.
Seed holder.
Okay, so initial state is, I guess we lost that. Initial state is boot. If anyone wants to look at my mini comments just to print out, and then also this LED. So right now it's in calibrate. So what the farmer would do is they would go to the seed tube, and the goal is to align it between this. You're trying to find a safe zone. I call it the neutral spot. So I'll just roll this till this axis is in between two of the holes, and then push the rotary encoder button. This is the user interface. And then it should go to step 2, which is this extractor one. And then we want to place that in the neutral position. The 45 degrees where neither of these two positions will actually contact the tube. And then there's the mode, which we're going to skip. That would actually allow me to add new or change the position of these implements. But we're going to turn and cycle through that. And then now it's the in-row spacing. So right now I have it set, I could go from 20 millimeters all the way up to 500. I'm going to use my default of 50 for this test, so 50 millimeter spacing. So once we click that, all the programs, it's ready to run. So now the encoder's right here. It references this wheel. So as this wheel advances, you'll see the state machine operate the actual vacuum. So if I go forward, that's position 1. And now you'll see on position 2, it's going to do the alternate spacing, and then position 1, and then position 2. So, and if I give it a little more speed, it will go quite along.
How fast can you go before it breaks?
Not that fast. I did give it a good whip, and it didn't stop. It just kept going, and it wouldn't abort. So that's a bug I need to solve down the road.
Is that your friend? Is he your friend?
Yeah.
Sam, does it move in this direction on the ground or that?
Yeah. So it would be advancing towards you.
Okay. So this would have the fins on it to open.
Exactly. Yeah. What Barry's referencing is the trough. So what I had imagined where there was going to be U-shaped fins around here, kind of like your device, that would actually set troughs where the seed would drop. Didn't quite get there, but we will eventually. So that's the.
How's the seed fed?
Seed fed? So that was another mechanical limitation. So originally, this was the seed trough. The seeds were supposed to be in here, and then have a tube that would come out of there to keep feeding that. This is my 4th iteration of this. In testing, it does pick up the seed, but what I failed to do is leave a gap here. So the seed never leaves the trough. It just gets knocked right back into it. So good intentions, but I didn't quite get there. But I did want to show is that this vacuum is capable of grabbing and holding the seeds. So the second test here is this fan. So it's going to get a little noisy here, but what I'm going to demonstrate is that this fan can actually pick up the seed and hold it, and I'll rotate it so you can see that. So this guy's going to start up here. And so these are cilantro seeds, just like a round, uniform seed. So the idea would be it would be in the trough. They get, collected right to the tube, and you can see they just get sucked right onto the tube. And then
Did you film mine on it?
No, I got to come up with a trough eventually. And then you could imagine as this rotates, this extractor would be lined up. And you can see it's a funnel bucket. It'll intercept that seed. And then you can see the seeds are on the, so it's got to actually pick up the seed and hold it there. Yep, that is as far as we've gotten with this vacuum seeder. So proof of concept. So we know the planting spacing can work, I can program it, and we know the vacuum is actually capable of picking up, rotating, and releasing the seeds. But there's further work to do with actually creating the right mechanical trough that optimizes that.
So it's got to be uniform on the seed, otherwise it won't hold?
Not necessarily. I've only tested with cilantro. Lettuce seed is kind of like a blade, So if the vacuum's strong enough, the lettuce will adhere to it, but there will still be air gaps. So it's
Okay.
future testing, but it doesn't need to be a perfect circle.
Okay, good.
But also, I was also thinking of putting some kind of steel catch in here, like you have in a water system, like a
Yeah.
micron filter, because I imagine some seeds will come down this pipe, and I don't want them to get up in the fan there and that fan. Yeah.
Some.
No, lab bench testing right now.
Those leader holes can get empty.
Well, this will always be above the dirt. The lowest point, these cogs will sit in the dirt, so this will always be above the soil.
By bricks?
No, if you let it down, this is just so I can spin the encoder freely. But yeah, normally these are actually contacting the ground, and this is rolling the bed flat, so it's prepped for seeding. And then they're actually, there's a reason this is so wide here is because there will actually be a literal drag chain. And because these seeds are so small and we're only going to a depth of 1/4 inch, that chain rolling across the surface will close those furrows, and then this will pack them down in the end. So,
Would you be able to do that demo again, but rotate
the
this
vacuum
and have it,
or this guy?
instead of
encoder?
moving the drum manually
Oh yeah. So
with the seeds?
Oh,
The
yeah,
vacuum?
yeah.
Yeah, I was gonna say I want to see the, because it looks like it should work.
Oh, I see,
fine
all
the way-
together with
yeah,
the vacuum.
yeah.
Okay, yeah, let me just, we'll start from boot there. So, okay, so this is, so anytime you can hit the pin during sampling, it'll abort, and then that puts you right back in calibration. So we'll just go right back to that routine. So we'll put that there. Then hit press, so that's the vacuum tube. And we align the extractor to neutral, neutral being the place that neither of those are contacting. Okay.
So these actually have to scrape the seed off the.
Exactly,
break the
yeah,
vacuum.
yeah, and hopefully I can demonstrate that here. Test mode, again, we'll skip that mode. And so now we're in program, we're gonna select that 50mm spacing. And now we're in the sampling regime. I'll power on the vacuum, and put some seeds on it. If anyone wants to add a few on that end to the tube, they can. So yeah, just see if those little blocks are.
Next time we come back, there'll be cilantro growing in the carpet.
Yeah. So we'll try with a couple here. I'll spin the encoder as if the machine was advancing. So yeah, we're not quite aligned there, but the ones that do will actually catch there. So. And I'm sure some will come around again here. So not quite, we need to work on alignment, but I do think it's possible.
Nice.
So Sam, is the idea basically that every one of these spots will get populated and then
Yeah,
this will
so
just
at any
scrape off
point
what
you're
you actually care about?
Yeah, exactly, and it'll just hold there if you're not using it. You know, if it doesn't get contacted, it'll just stay on the tube. And the idea is too, it'll help stabilize the vacuum. So any place that's not being used will hopefully collect seed, and that way it's less variation.
That's for the birds. Right. Why do we grow cilantro seeds? They taste better as a seed.
They're good, yeah. So that's actually called coriander if you eat it as a seed. Yeah. Yeah, no, I mean, yeah, that's you put that in all kinds of cooking.
That's why how coming in and eating your project.
Huh?
How do you feel about how coming in and eating your project?
There's probably 20,000 seeds. Okay. Out the demo. Does anyone have any additional questions? Oh no, it was catching up. Yeah, there's a bit of a lag. So if I could, no, it was just more because it was probably right at a drop point. But now if I go forward, oh, well, yeah. Thanks to debug still. I have that in the code. It's meant to ignore that. Like the decrement, it will actually decrement it. So it tracks how far it went backwards. What?
What's next?
Saw something over here. Observe. I know. It doesn't fit. I picked cilantro because they're perfectly like round, you know. So mine's a game. It ends up getting still. I'll need 8 people time, which I want to get stuck in. I knew you would. I had in my mind. I was like, I know. Yeah. Oh, that's awesome. Yeah. No, if you want a handful of we should do that. Yeah, whenever anytime. Get right to the live I'm really excited. Are you doubling me? No. I don't want parental controls. I want screen mirror. This. It's just oh, thank you. Ah. Alright. I got the command running. Oh, look, you crashed completely. That's fine though. Go to this. Just the ones you buy there are like
yeah. They said it's really well, I
Actually be in the correct.
Yeah, those are gonna do stuff. That's why I left them over there initially, and it ends in a game. So if it broke today and fixed it today while sitting here, so yeah, that's. I wanted that. I got to the end and like. Oh boy. Hi, my name is Evan Morse. I'm one of the last dying computer engineering students. I really wanted to come over here. I had the option of going software or hardware when I was doing my project, and like I got into this degree because I was already a programmer and dabbling in programming, and I wanted so bad to understand that boundary between hardware and software, and that's really where I wanted to live. I wanted to take my skills coding and make things that did things with it. And one thing that I really love are games and toys, and I think that they have a really important place in education. Not to speak ill of this school, but I have been, I've had a long life of feeling like education has really let me down in all of its systems, and really let a lot of people down in the way we teach things and how we teach things towards production and goals over understanding a lot of the time. And I think games are an incredible way in learning to teach things to an understanding kind of accidentally. So my product that I finished, they're called bit wands, but really what my project is about is about reinventing the wheel and doing it yourself and stepping against the common advice, which is don't reinvent the wheel. Use a system. Use something somebody else has done. Use the term that pops up all the time is use the industry standard. And unfortunately, industry standard actually just tends to mean who had the most money and marketed the best. And we live in an age of self-empowerment with computers. And so I really wanted to do this project, and I wanted to do it with zero dependencies. So this is a piece of hardware. I built every single piece of software from the ground up. My only dependencies are the programming language I wrote it in and the GCC compilers that built it into bytecode. See, that is my software malfunctioning and putting in the default picture instead of the picture of my wand. But you can see my wands here. I said no dependencies, I meant it. I built this software that I presented it in myself as well. But the bit wands themselves are binary state machine toys. They're really just to represent the concept of a bit. You know, you hold them up and it's on, you hold it down and it's off. And there's a ton of games that you can play with that. It started from an idea. I have been part of the Wisdom team, and one of the things that we've been doing every summer is we do these summer camps, these technology summer camps, and we did them for a few years. And we had this Arduino project that was overly complicated and was more just following a bulleted list, and the kids didn't really get anything out of it. And so this last year, after having read this book by Charles Petzold, Code, where he really breaks down the way binary systems work, I thought, well, what the hell? I'm going to bring in some flags, and we'll play some games where the kids are the bits, and we'll get them to think in base 2. And it was a huge hit. And so I decided when I got to this project, I was going to expand on that idea, not only in creating the game itself, but also creating a whole set of open source software underneath it that could be taken, expanded to make games like this, for other educators to make games like this for free. So the project stack
Well, it really got away from me. I would put a Gantt chart up there for you, but it would be a waste of all of our time. I did fill out a Gantt chart because it was a requirement of the project, but I very much knew that I was stepping into the realm of I don't know what I don't know when I started this project, and I knew it was a tunnel downwards. I didn't realize how much was between me and the firmware and how many times I kept going, well, if I want to do this project right, I got to build that too. And so we had Fig. Fig was a configuration language I spec'd and documented completely. Munch is a lexer and parser building library. Jig is a library that takes Fig files and turns them into static code to use in like a hardware extraction layer. Jig RP2040 is specifically Jig adapted for the RP2040. I've got Loom, which is a library of all the generic hardware libraries that I built, completely hardware agnostic. And then I have the RP2040 HAL, which is implementations of those Loom generic drivers. And then there's the firmware I wrote for this hardware right here. There's Framework Tool, which is the software that flashes it onto the software. I wrote that myself. And TermPres, which is this software that is a terminal presentation software, and I wrote this myself as well. I'll walk through the hardware. The wand itself is actually very straightforward. We have a basic power management system, which is just a charge controller and a variable boost to 5 volts, so I can have a 5-volt rail, which allows me to run my LED globe at the end. Everything else runs off of 3x3, which is stepped down by the RFM RP2040 here. And then I use an RFM69, which is a low-powered radio for all of the communication between devices. I have RP2040 hubs here, which communicate with those wands, and an accelerometer, which wakes the devices when they're moved and also helps them determine whether they're facing up or down. I guess I'm not speaking to this very well, am I? So the RP2040 itself, if you haven't worked with it, it's a great microcontroller, really high power. It's really great for working with all kinds of different communications protocols because it has this feature in it called the PIO cores, which are these really great machine cores, which are really tight-timed like communication protocols, which came in incredibly handy because LEDs tend to use this protocol called one wire, which nobody offers hardware to work with one wire, and typically you bit banged it. So within my software, you use the PIO cores, and it is controlled very tightly on hardware. The accelerometer, it's just a basic Axle 345 module accelerometer. It does 3 axes of acceleration. It just measures the force of gravity and force on 3 axes. And so when the device is standing still especially, it can tell very well which way it's down. Radio itself, the RF69 is just a great low-power radio. It's actually from these, it's a chipset made by the same company that makes the LoRa radios. I'm sure everybody's heard of LoRa, which is their proprietary system. And so I very much intentionally stayed away from the proprietary system and used their more open RFM69, which is actually chipset made by Hope RF. And then there's just simply the power systems. It's just it's a 1,000 milliamp hour battery, a charge controller, and we step it up to 5 volts so I can have that 5-volt rail for the LEDs. And then the LED globe itself, which is just a 3-piece of 1-wire LED segments. This is my rough bill of materials. My entire project came in at around $350. It was constantly changing. I bought a lot of small prototypes to try things. It took me a long time. It wasn't very many parts, but it took me a long time to figure out what I was going to do. I tried to come up with a physical way to do the accelerometer at first, and it just seemed like it wasn't going to work very well or be as responsive. And I wanted something really quick and responsive so that I could use them for a game. It would be responsive enough that it could be competitive. My battery life estimates with like a bright demo, it is now, if I left it on, it gets like 4 to 6 hours. With general usage, if you were teaching like one class a day and using it for 30 minutes at a time, you're going to get several days of battery life, and if they're used infrequently, it could be up to a week. So they hibernate really aggressively. Right now, they're actually in a really active state, just kind of show off. I did that on purpose, but typically they every 30 seconds they drop into a completely like hyper low power hibernation state where they live at about 400 microamps. All right, Fig. Fig is the bottom, is the first thing I did in this project was try to decide what data format, because the first thing I wanted to do was build a data-driven build system where I would define all of the hardware in data files and not in code initially. And so at first I was working in JSON, and I hate JSON. And I actually went through like 3 different file types, and so many of those file types, they all use indentation schemes, and you wind up 17 indentations across the file, and I hated it. So I designed Fig. It's completely flat. It's kind of like the TOML, if you've ever worked with a TOML file, but I added a lot of features to it that allow you to express hardware as like a first-class concept. You can see right here, there's a little bit of like syntax example. Well, I should have had. There's a couple more examples there. That you can do bit fields natively, all the numerics that you would expect in any programming language, and it specifically has a lot of language for representing registers and hardware, because that's what I needed. Then I had to build a parser, so I had to get from Fig to Zig. That's why I built the parser Munch. Example of the Fig file and what it comes out to on the other side. That's the schema it gets loaded into in Zig. If any of you hardware people haven't worked with Zig yet, please. It's beautiful. It's like C with sane features. Munch, so I was talking about Munch. Munch is my Lexer and parser library. It is a generic Lexer and parser library. I used it to build the Lexer and the parser that parses Fig to build the entire HAL for the system. The Lexer, the parser, I'm going to glaze past those. And then there's Jig. I promise I didn't make these rhyme on purpose. I named them on different days. I had been doing woodworking and had just made a jig. And it felt kind of like what I was doing, that I was building this frame that would create software for me with data. And so I called it Jig, and then I realized that I was using Jig with Fig and Zig. But I didn't change it because I hate myself. So Jig describes the hardware. It then parses all of those data files and validates them. It will not create bad code. It will invalidate any hardware that you've described illegally. And then it generates a really a very thin Zig hardware abstraction layer that's just for like register level access. There's another example of what the input and output looks like from Fig to Zig. And then I took Jig and I wrapped it one more time into Jig RP2040, and it's just that Jig build system that generated a great hardware abstraction layer for me. And then I had to wrap it in the specific way that the RP2040 has to be built, which is actually kind of a tricky device. It is a microcontroller that has its flash memory outside of its hardware, which means that the bootloader itself doesn't know the manufacturer or brand of the flash chip, which means you have to write your own bootloader that runs after their bootloader to load your code from the flash. And that was surprisingly tricky. It has to be in the first 256 bytes of your flash memory, and the fast 4 bytes of it have to be a CRC of the contents of that 256 bytes. And if it's not correct, then the device won't boot at all with 0 error messages, and you'll hate yourself. Yeah, it's this, exactly, the startup. The ROM, it starts with the ROM bootloader, and then it goes to boot 2, which is typically what it's called, and that's written by me, and I have to write that based on the flash chip on the board that I used. And so then ultimately I wound up writing a full-blown RP2040 HAL, well, really just as much as I needed to to get my system working, but I bring up systems, clocks, GPIO timers, power helpers, and then I had to do all the communication protocols I needed. I needed I2C, I needed SPI, I needed USB, CDC, which, by the way, is the hardest thing I've ever done in programming in my life. Never write a USB driver. I thought it was going to be a lot easier. And I took a very specific discipline with everything I designed because I had worked a lot with other vendor SDKs like ST's, HAL, and I've worked a lot with the Pico SDK, and I hate both of them because they're clearly code written by hardware people and they're very incomplete. And you run into a lot of problems where you run into a lot of stale state issues where the code changes a lot of things, hides what it changes, and then gives you no way to revert it back to what it was previously. So my entire HAL was built on this concept of all subsystems had an initialize and a deinitialize. And the initialize always confirmed initialization state, zeroed it to a known state, and then put it into a known working, like known starting state always. And deinitialize always brought it back to that same known zero state 100% of the time. So when you flipped back and forth between a init and deinit, like if you were hibernating the device, you always knew it would wake up and all your subsystems would wake up into the exact state that you wanted them to, which was the source of 2 bugs in the Pico SDK, which through the course of working this project, I was able to submit bug reports or bug fixes for. I didn't submit the actual fix, but I told them what was wrong with it because I was able to do it just by working up from the bottom, taking this really thorough init deinit discipline. I was able to find these bugs that were really just caused by poor state management and laziness in their code. Okay, so in the firmware, the most exciting thing that I built in the firmware, did you turn off? You silly, did you die? This would happen. Let's charge this while we're talking. The last feature I managed to get into this system was over-the-air firmware. It's really one of the things that was on my bucket list for this project, was being able to flash code to multiple devices at once wirelessly. For personal reasons and just because it was a interesting computer science challenge that I was kind of steered away from, and that's exactly how to get me to do something. So the wand itself, plug in so we can actually play this game afterwards. Yeah. So the wands themselves right now, they're white, and it's because they're in a waiting for firmware mode. They actually have nothing flashed on them currently, but their typical state machine operates. They are constantly probing when they are awake, whether they are up or they are down, and they send a message out to the hub. They hibernate aggressively. They're woken up by any activity over a threshold on the accelerometer. And that keeps them from using a lot of battery life, but also keeps them very responsive. The hub itself, which is just one of these, I had one built, but I nuked my, I over-soldered my poor RP2040, and I just happened to have another development board sitting around that had both the radio I was using and the microcontroller I was using, so I used that instead. This is actually a board designed by Amelia. But the receiver itself is the source of truth for the whole system. So the wand won't change its state unless it can communicate it and be confirmed by the receiver that the state was changed, so that they are always in parity. And then there was the USB CDC boundary, which is the CDC protocol is the simplest managed USB protocol. It operates like a classic UART serial connection. It is the simplest protocol other than just getting raw bytes off of a USB line. That's why I thought it was going to be an easy driver to write. and it took me about 5 weeks to debug that. I think it was probably the primary time commitment. I was doing other things at the same time, but that driver alone was probably the largest debugging time commitment. I had to come back to it many, many times, finding new bugs that would cause new problems. Difficult, very, very difficult. Rewarding, but difficult. The radio operates on a really simple send and ACK protocol. Any packet that's sent has to be ACKed. Otherwise, it's considered not sent, and they're a bit depending on what's being sent. There are protocols for how many times it's resent, how long it waits to resend. I tried to use good practices of what's called jitter and backoff, which is a technique for when you have multiple devices screaming into the void to one hub at a time. There's always that chance that they're going to get caught in the same loop and scream at the same time over and over again. So you have to have this concept called jitter, where they're always a little bit different in how long they wait, and back off, where they step back significant amounts of time as they are retrying. And that stops that collision process of every device screaming at the hub at the same time. I did use LLMs to work on this. 2 years ago, I probably would have said absolutely not. I used them too hard at one point. I tried to give it a piece of software to write. I learned very quickly. Let's see, did I write it? Yeah, not a system designer. It's stupid. It'll write the 10 lines of code you need, but don't let it write software. Don't let it make the decisions that a human makes. Don't let it decide where things go or how things happen. Very good syntax machine. Horrible programmer. I learned that the hard way. I'm pretty sure I cried at one point because I asked it to do one thing and didn't put the proper guards on it, and it changed like 500 lines of code in my code base. I wanted it to write one function, and I had to unwind that entire process, and it made me cry. Be careful. Great tools, but scary. And then there was this presentation software. This was kind of just a joke at the end almost, where I started my presentation about 2 weeks ago, and I realized it was about to be basically the first piece of software I was using that I hadn't written, so I decided to write that too. There are some newer terminal protocols that allow you to do variable text sizes in terminals, and so I didn't see any presentation software available in the terminal, so I wrote this. And it actually looks pretty good, I think. It's got a nice clean look. I've always been a huge fan of monospace text. But really, it's all about the kitty keyboard protocol and the the kitty graphics protocol. It sounds funny, but it's probably the most modern terminal that exists right now. Oh yeah, lessons learned. Scope control. The whole point of the project was to kind of drift out of scope, but I did not control it. There were things I would not do again. I don't think I would write the USB driver again in this project. I think I could have been, it would have been a much stronger project. I could have done a lot more with the end product itself if I hadn't spent so much time in the weeds. But I was happy to prove that I could do it. I wish I had planned a little bit more and thought a little bit more. I didn't know what I didn't know, but I also don't think I tried enough, and with some better effort, I could have come up with a better tree of projects and what I was going to come up with. Yeah, it would be nice if I hadn't been fixing the game slide of this literally an hour ago, sitting over there watching presentations. Don't add features to your project in the last week. Oh yeah, that's right there. Are we already here? Let's actually get it all going. It's actually
There we go. Anyway, so I built a Rebel to communicate with all the wands at once because they are meant to be a game system, so they have to be able to have different firmwares and abilities pushed onto them as a whole. So I've just selected wand 1 there. Let's go ahead and select wand 2. You'll see it filter around. I'm going to throw a selection on all of them. You'll see them all turned yellow. So this one. Did you tell me that you missed it? I did. Why is wand 5 unavailable? First time this has happened. Another time. That's neat. Oh, you missed this yellow paint too. the purple was better. There you are. All right. And install the quick test firmware on all of these. You'll see it go around, give it a little 2 green blink on them one at a time as that's wirelessly pushing a new program to each one of them. Select them all and run the software. I just pushed them. It's really simple for the initial thing. It's just going to blink that blue light for 10 seconds. Then they're going to return themselves back into that radio boot mode. Some meaningful software on there. These are a little fatter, so it's going to take a moment longer for each one. So I think a huge part of this project was proving that you can do complicated things. I am one student. This is about 6 months of, it's more like a year's worth of work, but it's like 6 months of hard work. And I like the world talks about projects like this, like it's millions of dollars of man hours, and you have to use the ST cube system because you waste all this time and money. But I found because I did this, I can debug, and it was like putting the features together is very fast, and that base level understanding is much more powerful than understanding how to use ST cube. There we go. Oh. Now let's put them into their actual game software. So this is them actually in their Bitwand program. So the whole point of Bitwand is that it operates inputs out. As it gets its hub, you'll see them all start to wake up to their orientation. It's gonna happen. First bug. Other things that it's never done before. What is this? We don't even believe for. Well, that hasn't happened once. This has been working 100% all day.
How many lines of code do you think you wrote for this entire thing?
Probably like 4,000 or 5,000. And it like that also includes like scripts, and then there's a lot of documentation written too. I've written incredible amount of documentation. And actually, like probably the greatest usage I've had out of LLMs was in documentation creation. It's really great for first pass documentation. Lets you like spend all the time that you want working on the code. Helps you get past difficult problems. But if you let it take the problems away from you, you find you can't solve the problems when they actually happen. So and there was this nice balance of it helping me learn things, but not doing things for me, or I could get myself in trouble very quickly. All right. Those. This way. We'll try this again. Oops. Why? Oh, why? What are you doing? Better over those. Yeah. Here we go. Take the program, please. There you go. Your job, would you? Don't know why we have lost our hub completely. It's gonna flash up software onto this one instead. I think one of my radios.
Problem one, number 7 being problem one.
No. No, in fact, I wish it was giving me any of the problems that I typically have, because then I might know how to fix them. But we are just well, I'm sorry. Sometime in the last 4 minutes, having not touched it and demoed it on the other side of the room, the end of my presentation broke. So maybe I'll go sit down and try and fix it and play the game afterwards. Any questions? I suppose.
Any questions for?
Oh yeah.
Real quick, is the when you flip them, is that your 0 and your 1?
Gee, it's supposed to be. See, and what's happening right now is that the wands themselves don't actually decide their own orientation. So you see they sit green because the wand has to confirm with the hub that it has changed its orientation, so it stays with the game. I don't know why the
they're
hub
changing color when it's like 1 and 0.
1 and 0, yeah. And so the game that I intend to play that was working when the wands were actually working. Oh, and that's what's happening. That's so funny. I'll bet that's it right there. I don't know. I don't know what's happening. It's just not. It's not talking to its hub now for some reason.
Some time and a little bit.
Yeah, I suppose so.
Yeah, if there are perhaps other radios of the same type.
I mean, yeah, but that wouldn't have any effect on them. Like they're recognizing their own specific protocol. And also I was sitting over there working fine. I have no idea what I changed. That shouldn't be hurting me. No.
Thank you, Evan. Our next presenter is Amelia. And we present.
Great. Hello, I'm Amelia, for those of you who I haven't met. I am primarily at the Randolph campus, but I'm doing this class up here this semester. I'm working on a snow groomer navigation system, actually, which is a small portion of a much larger initiative that's been happening at the Randolph campus. So I'll start with a little background on that, what I'm actually doing, and why. So overall, this kind of initiative that's going on down at Randolph is that we have pictured up here at the top right a ski slope. It's, I don't know, Kevin, do you know how tall it is? About 100 feet tall, and it's got a rope tow that's fully functional and certified that's been running since the 30s. It also has lighting everywhere, so it can be used 24/7. It doesn't have any snow generation, but we also can't groom the snow on it in any way at the moment because those vehicles are really big, really expensive. A sophomore mechanical engineering project last year, I believe it was, actually created a chassis for a snow groomer, a miniature snow groomer to use on this ski slope, so that students and community members can use this hill in more conditions. Basically, what they did was strap two snowmobile chassis together and put electric motors on them. It's got, I think it's 4 horsepower, so it's a pretty beefy machine, and you'll see it outside when I demo it. So more background on what it's actually doing. If anyone isn't familiar with how skiing and ski slopes work and snow grooming work, which I wasn't when I started this project, I've never been skiing. Essentially, a snow groomer is this like tractor-like vehicle that has a tiller on the back and a plow on the front, and it like flattens out and then roughs up the snow in a very specific way. In order to do that, obviously, it needs to go up and down the hill in a specific pattern to cover all of that area. So the project summary of my scope of this project and this semester's scope of this project. I've been working with two people from the Randolph campus, Keith Carrera and Luke Williams. And what they're working on is Luke is working on kind of the drive control system to manage the motors and a remote control system for this. Keith is working on some lighting and safety systems. And I'm working on actually automating the navigation itself. So my scope of this project is, as enumerated on the left here, to implement a modular navigation solution that can be used for this or other vehicles, such as maybe even Sam's Cedar, to drive it along predetermined paths, to also, using technology that I'll get into later, prove whether or not RTK-enhanced GPS is actually effective in projects of this scale and at this cost point. Provide a precision positioning system to the campus for future use, because I will also get into how GPS is enhanced with these RTK systems and how we can provide that enhancement to other people. And also, of course, to allow for these future projects and further expansion on this project for more sophisticated pathings and all sorts of things. The actual deliverables that I would like to demo are a GPS connection station, that's that RTK, which again, I will explain later, I promise, for the Randolph campus, and then a prototype of this navigation system installed on the snow groomer chassis to demonstrate that path following ability. And of course, a repository of the hardware and software, all open sourced, so that it can be used and improved upon in the future. Kind of a summary of how I've decided to work this. The solution is basically a PI controller. The controlled variable in this case, and I have a diagram here, the controlled variable is, of course, the direction that the vehicle is pointed. When you have a steering wheel or any sort of steering method, you control where it is, what direction you are pointing the vehicle in. Therefore, that angle difference between your intended path and where you're actually pointing becomes your proportional error term. So as you can see in this diagram, I've drawn kind of a vector-based navigation solution. What we do is we define a vector based on any one GPS point, which I will demonstrate later as well, and then an angle to that point, true heading on the Earth. This is all coordinate-based because it is happening with GPS and with the real Earth. So essentially, programmed into the snow groomer is a point and then a path, and you can have an array of these so that it does this path and then it goes there and loops around and covers all sorts of area. But you're just going to see it do one path today because I don't have a ski hill here. I didn't bring it with me, unfortunately. And basically, based on this target vector and the location of the snow groomer, we determine the direction that it's moving, find that proportional error term, the direction that it's moving versus the direction that it should be moving. And of course, because we don't want to follow a path parallel to this vector, we want to know that distance, the distance normal to that line, at a 90-degree angle, and that becomes actually our integral term. This was, as you can see down here, inspired by the VOR navigation system used in some aircraft. I think it's kind of being replaced by GPS, actually. But it's an instrument in your aircraft that shows you kind of in this middle dot where your plane is. Sometimes they draw a little plane there, it's cute. And then a path that is based on a vector you want to follow to a point which is actually a ground transmitting station. So it actually is very, very similar to how this works, which is why it inspired me to do it this way. Here's sort of a control system diagram of how this works with the rest of the snow groomer. So what's in blue here is in my system, the navigation system. What's in orange here lives in Luke's system, the drive control system, and the overall controller for the vehicle. So we have our pre-programmed path information that I described on the last slide, and we have our location and bearing measurement, which all comes from the GPS. From that, we produce those two error signals, which are sent to Luke's system, which turns those error signals into a differential signal to send to the right and left track to steer the vehicle. It is pretty simple as an overall high-level block diagram, at least. So that outputs two different speeds to each of the tracks, which become physical motion, which becomes a location and bearing measurement, etc. You know how a control system works, I hope, if you're in the same class as me. So I'll get into some of the underlying technology that I am using here, because I've said I'm using GPS, but I haven't explained why I've chosen GPS, or how we get such precision with it, because, well, that's on the next slide. So essentially, I chose GPS because I want this to be entirely modular. I want to be able to publish the designs for this and the code for this and have anyone be able to implement it in another snow groomer or in a seeder or something in their own field at their own ski slope. This means we need as little infrastructure as possible that I have to put up or that you have to put up if you are making this. GPS satellites are a lot of infrastructure, but luckily someone else already put them there for us. So I'm going to use those. And the way they work is that each GPS satellite, or in this case, GNSS, I'm going to start using the term GNSS, which is the Global Navigation Satellite System. I'm using that term specifically because GPS is the US version of that. It is 2026, and now we can use the entire GNSS constellation, which consists of GPS, which is the US version, Beidou, which is the Chinese version, GLONASS, the Russian one, and Galileo, the European one. So we actually now have 4 sets of satellites to use, and more satellites means more precision and more coverage, which is always good. The way they work is that each of these satellites transmits on a carrier frequency of somewhere between 1.2 and 1.6 gigahertz, a time code and some information about its orbit and about the orbits of other GPS and GNSS satellites. Based on this time code and information about, very precise information about where this satellite is in space, you can use what's called trilateration, which is the same as triangulation, but using distances instead of angles, to determine the point of this receiver in free space. If you have more satellites, that precision goes up. If you have clear skies and clear conditions, that precision goes further up. This is further complicated, though, by the fact that the US government actually intentionally reduces the accuracy of these signals so that they can use the precise sources for the military. So we don't actually get all of that. It's kind of stupid. But the important part then is that typical GNSS receivers, you get, in your phone, you get about 2 to 5 meters of accuracy. That's larger than the snow groomer, so this doesn't work. Luckily, well, there you go. You've got, a diagram of, where your receiver actually is, and then where you are actually receiving data based on atmospheric disturbances and all that. You're actually receiving the wrong signal for a different position, and then any additional error can be introduced in the GPS receiver itself. Anyway, we are going to use something called real-time kinematic positioning. We've got a cute little diagram here that Wikimedia provided to us. What this does is allowing us to use only one base station, which uses the same technology as the actual GPS receiver that we are, whose location we care about. We can correct this signal. If this base station knows exactly where it is on the Earth, which it does by either spending a really long time listening to satellites and figuring out over a period of days or weeks its precise location, or by being told in advance, which I did for you today so we don't have to wait days or weeks. It knows that location, it receives location data, and from its known very precise position and the data it receives, it can then extrapolate actual information about the atmospheric disturbances and other inaccuracies that it can convert to a correction signal that can then be transmitted to this rover, it's the base station rover, according to the RTK standard, to actually provide that same data without the rover having to do it itself. Because, if your rover is in a vehicle, you don't want it to have to sit still for a whole day every time it moves to get a precise location. So the base station does that for us, accumulates this really precise positioning fix, transmits that over to the rover, which then has in ideal conditions, 1 to 1.5 centimeter accuracy. which is crazy from satellites from space, honestly. So that's what we're going to implement here, and here's how we're going to do it. That's the same microcontroller you just heard Evan and Sam talking about, so I'm not going to explain too much about it. But we're going to use the uBlox ZX20P GNSS receiver. This is actually a brand new one that was released, I think, about a year ago. So nobody's really doing much with it yet, as far as I can tell. It's a hobby-grade receiver, but I have actually been able to test it and prove that it does, in fact, provide this 1.5 centimeter accuracy for about $220, which, 10, 15 years ago would have been completely unheard of, because that was, when that was cutting-edge technology, it was limited exclusively to the US military. And then I'm actually using that same radio that Evan was using for this previous demonstration to transmit that correction data from the base station to the rover station. So here's that radio link. It happens in the ISM band. That's the Industrial, Scientific, and Medical band. It's a few different bands that the FCC provides license-free as long as you keep it to a low power. For industrial, scientific, and medical devices. It's perfect for this application where we need a low power transmitter that operates at 915 megahertz, which allows us to have an antenna about that long. They're 100 milliwatt transmitters, and they can transmit a baud rate of 57.6K in this case, which is way overkill. Some implementation and testing that I've done then. For this navigation controller, I've done some testing on the Randolph campus, proved that the system is sound and it can follow a vector, which is what you are going to see today. We've also tried out a few different schemes of that control system with just a proportional controller, adding in the integral elements and tuning that controller to see how we could best get it to follow these paths. And I've also done some testing with the GNSS and RTK stuff on the Randolph campus and at my home. And I have actually, you know what? I wrote this yesterday that I have not yet reached that 1.5, but I have this morning, just in time to present this. Yay. So you are going to see that today, I hope. And I have proof that the correction signal that I'm sending can actually be received clearly as far as 3 kilometers away with clear terrain, no obstructions. So if I were to install this on top of this ski slope in Randolph, ideally it should cover the entire campus and most certainly at least the ski slope itself. And I have found that these, $200 hobby grade GNSS receivers, they are as accurate as they claim, and they're accurate to about 50 centimeters without that RTK correction, which I was very impressed by. So this is actually this is a very embedded software heavy project. There's a lot less electronic design that's gone into it. There's been a good bit of it, but it's a very software heavy project. So I just wanted to give kind of a glimpse into that, how everything I have been doing for the past semester has been string processing in C, which is the worst thing ever, as it turns out. Don't do that. But yeah, you can see at the top here on the left is that RTCM correction message all in hex it's 1023 bytes long, and I have to figure out how to send it with a radio that can only send 64 bytes at once. So there's some packetization and control going on there. And then you can see on the right what the actual navigation controller is working with. This is my debugging output. I didn't bother using a debug probe or anything. I just like printf statements for that. It helps me. So this is what I see on my computer when this is on the vehicle, and this is the actual feedback that it's producing at the end. I did design a PCB for this because turns out the snow groomer vibrates a lot, and when this is all installed on a breadboard, it shakes itself loose. That's not cool. So it's going to be on a PCB at the end. Luckily, the actual design for the rover and the base station, because the ZX20P GNSS receiver functions as both a rover and a base station, depending on how you configure it, I can just have Kevin print 2 of these, which I did, and I can use the exact same thing for both the base station and rover. Don't have to duplicate and then redesign hardware for it, which is nice. These are my prototype assemblies. You'll see them too. Here's a timeline. Like Evan said, I can make a Gantt chart and put it here in front of you. It doesn't mean too much. Personally, this is not personally, a Gantt chart is not the way I organize my projects, but this is basically an overall timeline of our project as a team down in Randolph. If anyone has any more questions, I'll cover that later, of course. And our budget, as you can see overall this semester, we've spent about $3,500. It's an expensive one. Quite a lot of that has been on motor drivers and motors, $2,000. But I have spent about $900 actually myself on the GNSS receivers and everything. Well, not of my money, of course, Kevin's money. Yeah. I have all my stuff up on a website here. It's not complete yet, but I promise by the end of the day tomorrow, I will have all the information as a complete write-up. There's a picture of the SNIG roomer assembled and everything running on the Randolph campus. And yeah, any questions? Go outside and see it? Oh.
Bring the boomer up. I can.
Bunch of things that I'm told to just power through. This is essentially so just like a drone or an RC car, I can drive it. It goes in circles. It's got my laptop on it, so I should probably be a little gentle. Yeah, so it can be totally manually controlled, but what I'm going to demonstrate for my project today is using this RTK corrections system, which if you come over here with the camera, you can see on this RTK module, there's a little white light on that says RTK. That and the fact that in one of the messages that it is printed, there's a number 4 there, that indicates a fixed RTK position. When that state is active, the standard specifies that the location accuracy it provides is no longer relevant. That is a full RTK 1.5 centimeter precision. So this knows of the antenna theoretically to an accuracy of 1.5 centimeters. You'd hope. That is dependent on the base station I have over here. As you can see, exactly the same thing. Feeding into the GPS module, spits out that RTK correction message into the microcontroller, which then sends it right back into this radio to transmit to that one. There's a couple options for how this works. Number one is you can configure this as survey in, where you can leave it in a fixed location for a day or so, and it will gather data, very confident in its location on the Earth. I got here this morning, so this has not been sitting here for a day. I helped it out by programming this GPS module and telling it exactly where it is, so that we don't have to wait all that time for this to provide that level of accuracy. What I find is that in survey in mode, it will produce an RTK fix very quickly, but because this base station has location uncertainty for a few hours to a day, the location of the rover will actually be off by a few meters, consistently in a very precise way, but it will be off. So what I'm going to do is I have pre-programmed into this, and I recorded this working earlier, so it should work again. Down that way, about past that first gutter, I've marked a point on a map, and I've programmed that into here, and I've told this to follow a path due north to that point. It's probably on the path right now, so I'm going to drive where it will not be on that path, and you can watch it drive to and then follow that path. And then stop when it reaches that reference. Nicer than the Cybertron. Oh, that is the Cybertron, my bad. 4K. Yeah, I know, look how fast that is. Actually.
Hey Sam, can you do me a huge favor and run in and grab my
switch over to the automated
charger?
position
It's
is
this barrel
little
plug
janky
with the
switch
white
here.
ring on it. It's sitting on the table.
I am no longer in control. Well, okay, maybe let's not do that.
I would risk.
We're back in manual mode, and we can try that one.
yeah, it's a really
Hello everyone, my name is Amra Zolj, and this is my senior project, Smart Solar Power Management System. So today, many portable and solar-powered systems need real-time monitoring to operate safely and efficiency, especially some like the companies. A power monitoring system helps user track battery level, battery usage, current flow, energy consumption while the system is running. So real-time monitoring can help prevent battery damage, defect, overload condition, and improve energy efficiency. So my project was designed to demonstrate how energy can be measured, monitored, and managed in a small DC power system. Also, this project demonstrates a simple and practical solution for smart energy monitoring and management in a real-world application. So the main objective for my project is to design and build a smart solar power management system that uses a microcontroller board, which allow to measure voltage, battery voltage, solar voltage, and load current, and display all that in real time using OLED screen. And also to implement USB communication for monitoring and debugging using TerraTherm software. There's a lot of goals that I would like to achieve, but one of the goals are like accurately calculate power and energy in real time, develop smart load control to protect the battery from deep discharging, and ensure the stable and reliable system operation during testing, and demonstrate the behavior of the system using different kind of loads, including the small DC motor and some power resistors. And also at the end to create a system that is going to be extendable for future sensor and loads. This is my Gantt chart. Again, like you guys mentioned before, it's really hard to track all this. But I can say that from the beginning, I focused on project proposal, project requirements, and bill of material. Then during the fall, I focused to do schematic in KiCad software. Then after that, I build my voltage divider and do some measurement and set up the current sensor, and also do some testing of the current measurement. After that, I build my my load driver, which is going to be like the MOSFET. And after the building all the hardware prototype, I do like the measurement, the one that are the main for my project, including the voltage, solar, power, and energy measurement. And I also added like as a challenging to a battery health indicator. After that, I focus on my code for the controlling smart load control, and to show all my data on the OLED display, and also using the TerraTherm software. And after the debugging and all fixing, my project was ready to create a PCB design that will help me to to organize all my wires. And now today I'm here for my final presentation, and I hope in the meantime I'm going to do my final report till the Friday. So this is my bill of material that helped me to track my cost. Honestly, my project was really cheap. I didn't have a lot to order. So on this table, there's like components that I use, description, the manufacturer part number, quantity, and the price. The main component that I use, they were like STM32 Nucleo board, current sensor, solar charger module, lithium battery, and solar panel. All other components I just borrow from our stock. Now let's talk about the system block diagram that is describing my project. So I will start with the solar panel that is providing power to charge my battery. Then the battery is connected to the voltage divider, which is the purpose to drop the voltage to a safety level so the STM32 can operate, and to show all data on the OLED screen. Then between the battery and the load, there is a current sensor, which is the purpose to measure current flowing through the load, and also at the end to communicate with my computer. I use a USB port. This here slide show the hardware implementation of my project. It includes a solar panel, a charging module, lithium battery, voltage divider, and MOSFET. So now on the next slides, I will just explain what each component is doing based on my project. So this here is a voltage divider. So I have two voltage divider because I measure battery voltage and also the solar voltage. So we can see that the middle point is connected to the STM32 microcontroller board. The top point is connected to the positive side of the voltage battery and the solar battery, and the bottom point is connected to the ground. Here we have a MOSFET that the main purpose is to control the load on and off, is acting like as a switch. And here there's a schematic, so we can see that the gate is connected to the microcontroller board. So source is connected to the ground, and drain is connected to the negative side of the load. And also here there is like between the gate and the ground, there's a pull-up down resistor that ensure that that stable off state of the load. This here picture showing the current sensor that I use for my project. We can see that that sensor is powered with the VCC 5 volt that I'm getting from the microcontroller board. V output is connected to the STM32 microcontroller board, and IP plus and IP minus is connected in series with the load. And the main purpose is to measure the current flowing through the load. This is the complete schematic of my system. I only add this charging module, so to make sure that I have all my components on my PCB design. And here's the PCB design that honestly I struggle a lot. First of all, like I didn't have a lot of experience, and I have a lot of mistakes. Like doing the preparation of this, I also learning at the same point, because I'm using this software for the first time. Also, I didn't know that all components need to be like a through hole. And first time I did them like on a pad, so it was like so hard to solder. And also my connection, like they are pretty like close, so it was so hard to solder all that elements. And another thing that Kevin suggests, so because of his machine, so I first picture was this one is good, but the first picture was all on the top layer and it should be on the bottom layer. So I fixed that. So yeah, so this is like my PCB design. So now here's some testing and the result of the testing. These are like OLED screens. So 2 loads I tested. Power resistor 30 ohm. At that point, there was like a voltage 3.47 volts. And I was getting 120.2 milliamp current, which is pretty good and match with the expected value. And on the other side, I use that small motor. So also I'm getting like I'm getting like I was getting 137.6 milliamp the current, which also like pretty close to expected value. Another testing that I use is like with the serial output testing using TerraTemp software. That's like a free software that you can like just install. And on that screen, I use another one like load. It's like now 50 ohm power resistor. And again, we can see like that based on the Ohm's law and the measured values, we see that they are pretty matching, so which means that my system is working correctly. Now, I will talk about a little bit software implementation. I need to mention this is not the whole code. This is just like because the whole code is pretty big, actually pretty long, and I just do like the partial one. That I think that these parts are really important since like they are based on all the measurements that I did for my project. So on the left side. So this is like the code for the battery and the solar voltage measurement. So ADS reads the analog voltage value, and since that value is reduced by the voltage divider circuit, in that case we can see that it's multiplied by the divider gain to get the actual voltage value. Same is like for the solar. And on the right side, we have the calculation of the current power and energy. First, we get like that current raw, like the value that is we need to include offsite and sensitivity to get that value, and then after that we are getting the real value of the current. And when we have a current, then we can measure a power. And here we have the energy. Energy calculations provide over time to get like the power measurement, and that is updating constantly to get like to get energy in watt hour using like systematic sensor. For the enclosure, honestly, my project is pretty like let's say easy from that side. So what I only use like enclosure designed to protect electronics that I have inside, and I have some opening for the OLED screen, also for the push buttons, and for the breadboard that I'm gonna put like all the loads which I'm gonna test. And ventilation, it's already there, like it's a lot of holes considered for heat dissipation, and of course it's a compact layout for portability. And the whole point is of my project to design and implement a smart power monitoring system that will successfully measure the voltage, current, power, and energy. And hardware parts like a voltage divider, current sensor, and MOSFET work correctly, showing all that results in a real time, which means the system provides reliable real-time monitoring. The future work that we can do is to improve PCB design, definitely, enhance accuracy with better calibration, and add data logging or wireless monitoring, since now I'm just using like the serial USB port. And I don't know, guys, any question, so we can start the demonstration. The solar panel. So right now I'm using like 6-volt power, like the solar panel, and because of that, you're gonna see, guys, that I'm using pretty small loads, because like the 6 volts is like nothing, and I also have at home like the 12 volts. That's like 2 in the serial. I could use that, but then I need to change the battery. You can do that, but I decide this time I'm gonna focus on the small loads, and but you can wherever you want. I think it depends just like I said, like you can use like 12, 24 volts like solar panel. I use like the smallest one, honestly. And right now you cannot do that because my battery is also like just 3.7. So so yeah, I need to change the whole setup. Not a lot, but yeah.
Gary, where do you see these been applied? Where do you see this as being applied?
Oh yeah, so the reason why I decide for this, probably you guys see like that all like meters for the for the power meters, And then, and in that case, they use like wireless. So yeah, I use like just USB port, but they use like the wireless, so they are like measuring power, measuring energy. And it's like pretty like good. For example, if you have, I don't know, let's say somebody is, they order a couple solar panel on the roof, and they want to see like how many they have like the power that, for example, to see is there like some power that, is wasting. So, there's like so many like devices that, you can calculate how many powers they're going to consume. And then in that case, you're going to choose the solar panel based on that. It's pretty, now, I think now these days, since, a lot of people are using solar panel, because it's like better for the environment. And that's a really expensive cost. In that case, they want to know, okay, so then I'm going to calculate all my devices, how many energy and power they are like consuming, so I can choose the right, like the power panel. And so that's kind of like thing that, I was thinking, okay, maybe like for my project, I can do that. And honestly, I like this field, like something to work with the solar energy. I hope that in the future I'm going to be able to work in that major, in that field.
If you're able to like continue working on this project, what would be like an outlook? Would it be like a solar charging station for public use, or?
Honestly, I was thinking about that. So even like maybe in the future, my goal is like to build a power plant. So which is really good, because it's not a lot of work, and maybe on the beginning you have like some investment, but later like after a couple like years, you get all that money back. It's like there's like not a lot of work, and you can just also like selling energy to somebody else, or even for your usage, for your home. Or I don't know, maybe at the beginning some small solar power plant, and then later you can like sell to, I don't know, like to Burlington Electra or wherever, I don't know. This is just example. But yeah, I think it's really good, because this project is just like small project, and like it's just like a basic thing. But generally, like we use that the whole time, and like in our like real life.
Thank you very much.
Thank you, guys.
The demonstration for us.
Of course. It's honestly not a lot to demonstrate, but yeah. So I think I already demonstrate all on over there, like on my slides. But let me try to do that here. First of all, I always have some. That's me. It wouldn't be me if I don't have any issue. So this here battery. So last time I worked with my project, and it's got discharged. And then, like I came here, and it was like 0 point something. And I figured out, okay, because my threshold, like 2 point something, is not going to work. My, like my MOS is going to be off all the time. And then, I got a new one, like new battery. And at home, from some reason, I changed them, but they were like, again, like point something, like the volt. And now, Thomas told me, like, do you want me to charge the battery? And he said, they are like good, like 3 point something. And now it should working, but I did change my threshold because it was 2 point something. But it should be 2.8 that my, MOSFET working properly. So here I have, so I have here OLED screen. And I hook up some like loads here. So this board, I need to mention, there's a lot of wires here. So this is like my PCB board, which looks ugly. So honestly, because my soldering skills are like so bad, so it didn't work. So yeah, I think like the design is good, but just like my soldering skills like make it like really ugly. And also the another thing, so I didn't think about that. Here I have the current sensor, but I totally forgot that I need to have chip here, which I didn't order. And I know that I don't have time to order it, and so then I said, okay, so I'm just gonna do like a demo on with using like the breadboard. So here, so I already hook up here like one. This is like 30 ohm power resistor, and let me. Yes, that's a load. So I already have like some other loads here. This is my cord that I use. Like I use STM32 microcontroller board, and let me just start this. I already got the cold. I can feel that. Oh my God, which is not good. And then I have here also TerraTherm. So the TerraTherm is showing the whole the same results as on the OLED screen, except you can play a little bit more with like there's like no restriction on the data that you can put over there compared to here, because this is pretty small, and also like it's good for the debugging and like the fixing. I'm gonna just set up this. We need to change the another serial port. Okay, so now, so when I press this here, so now it's off, and you see like everything is 0. So when I do this, it's on, and you see like the changing of the current. Everything is changing.
Can you stop the flash?
No, I can do that, but I didn't, like because it's like doing the update all the time. I think we can do it on the code that, yeah, but it's showing like the good results, and the only thing here, so when I do like I'm just gonna put on off with this one. This is like the motor. This is just for this purpose, the really small one. And even I don't know, like I didn't figure out. It's gonna be so.
There you go.
I think it's like I'm not sure which one is like plus and minus, or even I think it's opposite. I also think like it doesn't matter, but sometimes it doesn't. And when I press on, it is showing like I think this is like the accurate value. But the only thing is like not spinning. It's maybe spinning. Maybe the current is not too big. Which honestly I think that's the issue, because when we see like the current is pretty like low. So that's the reason why it's not. And also my 2 point something so it's pretty low.
Yeah.
But it is showing like some, because it's spinning like pretty like small like, but I think because of the current. If I have like the better current and the better voltage, probably would be different. And if you see like here, like there is some data, and in this also I include the offset value, and I also current that's the current that is like strictly from the current sensor, and then like it's gonna transfer to the STM32 microcontroller board. But I think that's just because of that. My setup is like pretty like I said, right now I'm using like input like pretty low, so that's the reason why I barely have like I couldn't choose like the right load. Since like all loads like 5 and up, and this I could use like resistor and like this small like DC motor. All other, even like I find one of my daughter. I couldn't do it because it was like I think 6 volts, which didn't work. So yeah, so it's like I said, my project is like it's pretty simple. It's like I said, demonstrate everything what we are having in real time. Maybe a little bit like more developed, but that the whole point of this project to demonstrate how like device is converting like from current to power, and we have energy, and you know like how is MOSFET working. So you know like when it's off there's nothing. So when it's pressed like there's current flowing through, and you know like also this third term. It also can be like wireless. Right now I'm using like a USB port, but this is something like in advance. And don't look at my clothes, they're ugly, but yeah.
It works.
But I'm glad that because under there's like a lot of wires. I even don't know how this works. I was just like, okay, please just work that day, and then I don't care. Because out like it's horrible. And my husband helped me to like do this because I'm really not good in mechanical, like cutting and all that. But yeah, this is like my demonstration. I hope that you guys like it, and feel free to ask any questions if you have.
Any further comments or questions?
Are you gonna upgrade it so you can charge your phone?
I will, definitely. I will, because I already working on it. Like I want to do something, you know, like because for me that solar power is so interesting. I just you know like I want to use yeah you know even now I said like oh you can you know like charge battery like with this. My husband said no I have like something else. No try my you know like this is interesting. I just you know like I'm excited to do something like with this. And like I said, I hope you know like it's gonna be something in this too like for my future to work with. But yeah, I learn a lot of things.
Good.
Thank you guys. I just want to say I really appreciate for all your support. Thank you so much for all of these 2 years that we worked together, and thank you first like to Thomas. I know like I like you guys all, but he is my favorite. Sorry because during these 2 years he did help me a lot. Whenever I need something, you know, like I need to mention him like specifically. Thank you so much. I really appreciate. And like,
Did he show you how to solder?
no. But that's okay. But yeah, thank you really all because I know it's really hard to be like only one like woman in this group. You know, like I kind of feel like proud that I get here, and you know, like you guys all accepted me in this group, small group, which I really like it. You know, like I could ask you like anytime, anything. You guys always like help me. So thank you so much for your support, and of course, Professor, thank you. And like Ralph, he's the first person who you know like who I came to, and you know like he helped me, he believed in me, he told me you can do it, and you know like I really appreciate that because you know like when I till the moment when I got here, it was so hard for me because I kind of have feeling that nobody believed in me because you know like you come here and they're expecting okay so you know like. You are coming from the small area where maybe you know like what knowledge you have, you know like are you what you're gonna do here, you know like do you know like the language? It's a lot of barrier, but thanks God, you know like I did it, and thanks to all of you guys, I really appreciate like all support because you know like without you guys, I don't know, am I gonna do all you know like it's. When you have a support, it's really everything sounds like much easier to do, and you know, like, and then you just start believing in yourself that you can do it wherever. There is no like any like you know like there's no any barrier that you know like there's like over there like at the end that they are stopping you from achieving your goal. And thank you so much.
Good job, Jewish definitely helped me.
I know, like I know that you guys helped me.
this is my project. This is the Smash Foil Home Assistant. So this will be like a bunch of systems going together. Use the Raspberry Pi, the OpenAI, and the OLED and the GPIO control. Okay. So this project is for active home assistant. The idea is to use the Raspberry Pi as a controller and have some kind of the AI to control the electrical device and have kind of the text, the spec to ship back. So the object and wire. So the first thing it needs to be working. When we speak to the Raspberry Pi, it should speak back to you and they active the electrical device, and that's pretty much all of it. And the whole thing is run by the OpenAI for the transcription, for the text to speak, and I have an OLED to debug. So this thing can control the fan and the ALD. So why the customer want this? So this is the Python open store code. It's very easy to modify. So wake up OLD feedback and physical inputs. So the customer should be easy to change them any type they want. So the wire combine. So this is the very low cost machine. So total like $60, maybe 50, and they support the AI conversation. You can control all kind of electrical device. So I do it like 4 different layers when doing. So wake up layer to handle voice sensor, the runtime Python, which is Raspberry Pi for the Python handle, the AI, and the output with all of this, with all of the ALD and the fan. The flow chart. Can you click on the link for me? Yeah. Just scroll down, it should be a flow chart. Yeah. Okay, thank you. So this is the flow chart, the system. So right now, in the device, this is the idle, the assistant is waiting. So we don't say, I can speak right now, but there's nothing listening right now, so it doesn't trigger anything. So when the user say, hello robot, okay. It starts. So reset. Start that one, it trigger, it will start a section, and it start record the user speak, and it will send to the OpenAI. So the OpenAI will decide what the user asks. So could you scroll down a little bit? So the system now we know is if you want to active the fan or the line, they want to change agent or not. They want to like just the normal conversation, and they generate the speak to how they open that, and to like respond to what you say. Just keep scrolling. Then you want to decide what action you want to do. Turn on the fan, turn off the fan, or just keep listening. And this experiment to look back if like delay for a certain time. Okay. Can you come back to my presentation? You just come back to the, yes. So the main loop. So basically is what I just say. So for every 525 seconds, the audio and the voice sensor will just report constantly. And when you say that the word is going to be like the ID number 2 and active the device. And if you say the word reset, it's going to be the ID 82. with the voice sensor ready for me. This may expand the code how all of this work. So I have two main code for the system. So this is the launcher, the thing we're going to be run right now. So every time it run, it's going to be to display the OLED display and the voice sensor, and run the big brand of time. So yep, that's the wake up work to the at the code. So very much what I just explained earlier. And this the big code, the main function of my system. So so the original plan is just do like I original plan to let I agent to control everything, but it takes a long time to run. So I have to use the session to do the actually take active the GPIO. So the OpenAI does not directly control the Python. It's the Python we execute the action. The OpenAI will just run the Python. So this is the JSON I map out. So if target have the fan on this, it's going to turn on, and it's not reply turn on the fan. So and this the GPIO is going to be to turn on the fan for the 16, red light 20, green light 21. So the system have multiple agents, and I control them by the software guy, Python. So I use the Python to create a different agent MD right here. So inside each of the file, they have an agent to do the different tasks, and I just call them into hey, this guy named David. This use the Python to control, and this the guy who control the electrical device. So the magical push, so pretty much very simple electrical device. There's to Raspberry Pi, then the OLED, the voice sensor, some relay, the fan, the 9-volt battery. So kind of what is supply, put everything together. I know it looks like a mess, but so that's basically what I just say. So throughout the bin and the map layout I put. So for the ALD, I use the open source called Lunar ALD, which can pay animation, which is nice. And this is what didn't work out. So the original plan is to have everything run locally in the Raspberry Pi 4. So I did insert all of this so it just can run in the Raspberry Pi 4. So the first, which is the original, and I come up, kind of the real-time text to speak, speak to text. So it comes to real-time, it didn't work out very good. So I switch to the whisper, which is kind of to record the voice, and then you turn the record to the text. I did try the Piper, and it got it work to the Raspberry Pi 4 too, but into test machine too. But when I put them together, it doesn't run very fast. So I just switch to the online OpenAI and test the local LLM too. But this is the most heavy thing, and there's no way I can run a Raspberry Pi 3. So yeah, the Raspberry 3 is very low RAM, and it cannot really do a lot of things. Back. So this just and take a picture in my PC. So this is what the open core, the Python core look like. So I have all kind of information to decide the identity of the AI agent. So and this is how I debug all the code. This is not the way we support to do it, but at least it work. So basically, I just do make a Python code in my PC and send them to the Raspberry Pi. So the result, the wake up command work, the IOD do all the status report, the OpenAI and response work, and I can restore them anytime. But the piper, I did test them in the Raspberry Pi, but couldn't bring them together, the system, the power of them, the way too heavy to see the Raspberry Pi 3. So it's one lesson learned. So so the USB audio, this like give me a lot of trouble because like the port is random restart when I reset the system. So it took me a while to figure out how it works. And the port is not very good to the kind of application. It's like very fast, but produce a lot of noise. And I have to change to the Raspberry Pi 3, and this kind of not what I expect to go with originally. So that hardware. This is the build material. Yeah, I barely send anything into this project. So this one from Kelvin. This one is $20. The USB LED display. Pretty much everything can be found in the VTC. So the future informant. So if possible, I would like to order a new Raspberry Pi 4 so I can go with the original project. I did got the CAD design, but I didn't have time to bring it out. And yeah, so now the raw block is the speed. So this thing take the long time to respond. So this like the final conclusion of my project. Yep. I think my computer is not 5.4 coming now.
Okay.
So original, I didn't use this thing. Okay.
So you're using the Raspberry Pi 3. If you use have you looked into using the 4 or the new V5? Would that make running any of the AI software faster or easier?
Yeah, all of them run before I break it. So yeah, I can say it's very much real time if you do test the machine. This one can barely run it. So
okay. Okay.
It's no question. I just go now to the that's it. So you can say about the same as what I told the guy on the Thursday last week. So the first line with the agent name. So I named her Rose Better. So drop the AI assistant. So the network is connect to the network in my phone right now. And the status right now the idle. So nothing doing right now. So I did change two things. But I remove the what you call the strict AI agent command they will make. So right now it's doesn't have to like anymore. So if you like hello robot, can you turn off the red light? So this doesn't have to any kind of question anymore. So right now you see change scripting. It's sent to the AI. The agent speaking.
Turning off the red light.
Well, that's enough. So so another thing is when you say any hello robot again, it's automatically start to be, so we don't have to like wait until it anymore. So right now,
Could you say that again?
Hello robot. When you turn on the green light for 5 seconds, it's kind of have some kind of logic on it, so it can control the IoT. Some kind of logic like blinking for 5 seconds, delay. Yeah, I think I got it.
Turning on the green light for 5 seconds.
Oh, yeah, it's on. It's on. So the now.
Nice.
Okay. So this now got now like what device on right now. Now the state of the machine. So hello,
Which
robot.
device would you like to turn on? Fan, red light, or green light?
Can you turn on everything? What? No, didn't go. Okay. Hello, robot. Can you turn on everything? Oh no, it's it got it. So, yeah, I just want to do that. Now let's turn on everything right now.
Turning on all devices.
Hello, robot. Hello, robot. No, didn't do it. Hello, robot. Okay. What device is on right now? It should tell you like what device.
Right now, the fan is on, the red light is on, and the green light is on.
So let's try the strict action command I took my this morning. Hello, robot. Hello, robot. Then done. I want to strict action. You want to strict agent. Okay, this is got. So I now wait for it got the last line.
Which AI agent would you like to choose? You can choose Rose Carter, the AI assistant, David Miller, the comedian, Maya Chen, the AI newsreader, or Andrew Lee, the translator. Say the full name or say number 1, number 2, number 3, or number 4.
Number 1. Yeah, that's it's need to move forward. That's thanks for help.
So did this run pretty fast on the Pi 4?
Yeah.
Yeah.
Which AI agent would you like to choose? You can choose Rose Carter, the AI assistant, David Miller, the comedian, Maya Chen, the AI newsreader, or Andrew Lee, the translator. Say the full name or say number 1, number 2, number 3, or number 4.
Number 1.
Running out of here.
It is like to the system from to like to speak very fast and very fine method, so it have like emotion. Go crazy.
Switch to Rose Carter. Rose Carter is your AI assistant.
I just said to them.
So John, is it only recognize your voice or
Everybody follows that.
oh okay.
When I try.
I don't know what to ask. Hey robot. Hey
Yes,
robot.
Charlie. It mostly recognizes my voice.
Oh my god.
Doesn't recognize me. I told you. And I was planning to ask her something nice, but that's okay. And she's mad. I can see that.
Can you like have it tell it?
Thank you. Glad you like it.
I don't like it. Oh my god, it's annoying.
So when you say they set in every style, everything.
So when you get a response from like the API, could you have it like tell a joke or something?
Could you say that again?
Hello, robot. Hello, robot. Tell me a joke.
It's a cool project. I like it.
Why did the robot go to the beach? To surf the net!
Guys, that's my project.
And we have extra food up here, so please feel free to take some home with you, take some water with you. Thank you all very much for presenting your projects. Some excellent projects today. I know you guys put in a lot of work, a lot of effort, and many hours on your projects. And I thought everyone did a very nice job, and I think we impressed our friends from Hazlet Swift Casting, and hopefully we'll be able to put the rest of the bells and whistles on the project and get it going according to Dan. I guess the old rat tool is on borrowed time, so. Well, it's in front of it to be a grant and make sure the old tool is going to work. So, Evan, I'll take it from here.
Yeah, it's working out. Figured out the problem. I need 8 people. I need 8 people. And all of those ones. Yeah.
Do we leave for now, or
where did the Ethernet cable run off?
Did you have one before?
No, I stole one that was hanging around over here.
Right.
Your charger?
So, I mean, I've always been connected to this one.
What was the one that I thieved from before?
The charger?
No, the HDMI.
HDMI, you said Ethernet.
Oh, did I?
Yeah.
It's good old terrain. Grabbing at words. What?
Don't put your finger down. Yeah, I'll bet you like that. It's a proper guy. Yeah, those things are meant to be in circle.
Let's see, maybe.
1-1.
Oh, yeah. I know you're making it go hot. Oh,
This one, female.
We got this plan too.
you betrayed us.
What do you want to do?
4, 5, 6, 7.
My team.
It's right here. So you want to watch over here.
That's right. Oh, I see this.
Oh, I'm right. So you are in numeric order. The lowest number on your team is going to be the most significant.
Oh, okay.
So I'm last.
Fun.
Go right there.
Oh.
I am the most significant bid.
Okay.
So I'm
Okay. I think you and
Yeah, I mean, I can put some challenge on.
you're 3. You're
I just want to also be something else. So our team has to be 2. So that
2.
but
Dude, that's me. Oh, just me. Everybody else turn your thing over.
yellow wins.
Score 1.
Boom.
Let's go, baby.
1 for yellow.
I didn't match it.
So
is that
okay, so
Boom.
you are so to explain to you, you each represent 1 bit in a hexadecimal digit. It's telling you what you need to match as a team to be the right bits to be 2. We won. Okay, so hit space again. It'll pump for the other one.
9? What is that? Oh, it's 9.
It's me the one.
It goes there, but
Yeah, you did it.
Oh, we won.
okay, 1.
It was 1 0 1.
Yeah.
No, 1 0 0.
Okay.
Alright.
All right, hit space when you guys.
You guys, so yeah, hold the correct state for 1 second. You get the point as a team. I hit it again.
For a second.
Yeah, 1 second. You have to be stable for 1 second. So you can't just play a little.
What is? Oh my God! What to see?
He's 12.
No, west side. That's me.
8, 4. That should be it.
Is it C? I don't think it was
See,
C.
it needs some aggressive music and some flashing colors.
Yeah.
If you added the chromatic scale to these.
Yeah.
Might happen. Well, it doesn't even need to be a good scale. It's going to be a regular scale.
Yeah, that's a great idea.
That would
Yeah.
be the fantastic.
More time, the next thing I was going to do was make it noisy, so that had some sound. It was
What is that? One,
Two more going. I'm done.
2 and
I'm
4.
a
Boom, yellow.
Oh yeah.
Dominant.
very good.
We already lost.
No, you already lost. Yellow.
6. What's
That's me. I need not online. I need US.
That's 8 and 2. That's 6.
That's right. 4 and 2. 4 technically. What? You got it. It's actually hard to. It's hard to think as a bit.
This, yeah.
I can't leave school.
Hit it again.
5. What is 5?
One less than last.
5.
You,
Yeah.
Almost got it. We got it.
No,
I think we got it. 7. Oh,
Let's
go.
I'll be here forever.
Okay, I want to see you.
Okay, I'll be here.
Also, out to the west, so you got dancing with your heads.
It's just asleep. Wait, just tap it. It just wakes up. Yeah. It just drops its apple colors.
No, I'm 8. You're 4.
No, I'm 1.
Yeah, but there's the initial number on here.
What number are you?
8.
So you're not even standing in the right order.
No.
And look, you're marked here.
Yeah.
First, it's just like we were saying.
Yeah. Probably confusing yourself by standing in the wrong.
Yeah, we are in the wrong.
Yes. This one's already over. I wasn't even looking at the numbers.
Keep standing.
Wow, I'm just happy it works.
It's
pretty well.
Really reactive.
What's your game? If you change the whole time, it has to be correct for one of the teams.
Yeah, I think maybe increase the threshold.
I think 1 second.
Yeah, so probably 2 or 3
Yeah.
seconds.
Yeah.
Second.
The score from somebody.
Yeah. What is it? I got this working in the last week, so. It's on a terminal too.
11.
It's 11.
It's 11.
It's 11.
2.
Oh, we don't know it.
There we go. Okay. West got I'm a few years old. You did this in August.
I think 1-1-1. 0
binary.
1-0.
It is.
So we can prepare to know like.
I was about to. I need my cheat sheet for this.
It's 0-1.
0.
You don't know your hits.
Well, what?
I used to.
I thought we already
when we took the coding class.
Purple 1 round already.
Yeah.
What?
Oh.
0, 0, 0, 0.
0, 0, 0.
No, I cut the news over.
Yeah.
No.
And that was entirely the reason I made the game. It's like the whole reason I did it. The thing I did with the kids wasn't this exactly, but it was I gave each of them a flag and I kept asking them questions. And I was like, now try to figure out how to communicate without saying anything. Now don't even use your body. All you have is this flag. Lift it up and lift it down. What do you do? Almost everybody comes up with Morse code if they've heard of it. And that's like a great way because that's the first binary system most people are exposed to. So, yeah.
Why?
I'll expand this to a little collection of binary based.
0, 0, 0, 0, 3. Are you kidding me?
My bad.
Oh,
Let's do 0. The next one was.
Yeah.
Very cool. I was actually the threshold for the so it doesn't change until you almost reach the stadium.
Yeah, and it has to, because it gets confused of a quick swing. It wants to think it's down because it'll see that as gravity. So you have to like catch huge bursts in acceleration and ignore them, but watch them and resample them again later to see if it was a turn or if it was just like a. Because you'll see when I first programmed it, this would turn it red until it stopped, and now it won't do.
So when do you resample? Do you resample the acceleration once it's like dropped below a certain amount of acceleration?
It's about, I can't remember what I settled on. I think there's a 20 millisecond window before when it takes what it thinks is a correct value, and then it waits 20 milliseconds and then catches the next pulse coming in from the accelerometer. Because when it's awake, it's getting like 8 pulses from the accelerometer a second. And when it's sleeping, it gets nothing. The accelerometer is programmed to interrupt on a certain threshold, and so that's why it goes to sleep. It's backed up. Yeah,
that's cool.
And that's what gives it a much nicer battery life. Otherwise, these eat this battery very quickly. Like when I leave it in like flash mode, like I did before, which is just a super bright LED, they have like a 1-minute battery life. But when you turn them on and off like this, they can be managed. It's closer to 6 hours, 8 hours.
That's pretty good. That's cool.
I don't think I can do that for 16 hours.
It's not for kids to hit each other.
Welcome to the Bit 1 Enduro Championships.
I got friend, there's a timer at the bottom too.
What's that?
That's super cool.
Cool. And it's just a slide in the slideshow too. That's what I wanted to be, so that you could put an app you could drop right into the
I love this discussion right now.
Yeah.
Bring me back to C programming.
I only know 0.
Anyway, good job, man. It's tough. I think they're just
You can break it. They use so many pieces from the packaging. All the microcontrollers came in these stupid decadent packages. They did their own thing.
Plug. You see the rest inside, and that's the plug. Pull the whole thing down inside. Don't catch the cable parts.
Well, that's good.